Ever wondered how your favorite snacks are made? In this behind-the-scenes look, we explore the high-tech factories and intricate processes behind Krispy Kreme donuts, M&Ms, and Pringles. From mixing and molding to frying and packaging, discover the precision and innovation that transform simple ingredients into the iconic treats we know and love. It all begins, unsurprisingly, with flour. Krispy Kreme uses a proprietary blend of enriched wheat flour, one formulated specifically for its lightness, protein balance, and ability to yield that signature fluffy bite. The flour is sourced from select mills that maintain tight quality control standards, ensuring the particle size, protein content, and gluten strength all fall within strict tolerances. Once delivered to the facility, the flour is stored in stainless steel silos under controlled temperature and humidity, preventing clumping and spoilage. Next, there's yeast, the biological engine behind the dough's rise. Krispy Kreme uses a commercial strain of baker's yeast known for its rapid activation, consistent fermentation profile, and neutral flavor. The yeast is usually delivered in refrigerated blocks or vacuum-sealed pouches to ensure maximum viability. Alongside the yeast, the other raw ingredients include non-fat dry milk powder, high-stability vegetable shortening, dextrose, salt, and water. Each of these ingredients plays a crucial role in shaping the final taste and texture of the donut. The shortening provides mouthfeel and moisture retention, while the dry milk lends a creamy undertone and enhances browning during frying. In the mixing phase, the ingredients are loaded into a spiral or planetary industrial mixer. The water is typically warmed to around 95 to 105 degrees Celsius before being introduced to activate the yeast. The mixer operates on a timed cycle, first gently combining the dry and wet components, then increasing speed to develop gluten and build dough structure. The dough is mixed until it achieves a smooth, elastic consistency with careful monitoring of temperature and hydration levels. If the dough becomes too warm, it risks overproofing, too cold, and fermentation is delayed. Sensors in the mixing bowl monitor the dough's internal temperature, moisture content, and even CO2 output to ensure consistency. Once the dough is formed, it enters the bulk fermentation phase. Giant stainless steel troughs, called dough rests, hold the dough as it ferments for the first time. During this period, the yeast metabolizes sugars and starches, producing carbon dioxide and ethanol. This expands the dough and begins developing its light, spongy structure. Krispy Kreme controls this step precisely, maintaining a temperature of around 80 degrees and 85% relative humidity in the proofing room. The dough rests here for approximately 30 to 40 minutes, depending on the batch size and ambient conditions. After bulk fermentation, the dough is transferred to a sheeting system. This is where things start to get visually impressive. The dough is rolled and flattened by calibrated rollers until it reaches a uniform thickness, typically between 10 to 12 millimeters. From here, it enters the cutting stage. A rotary die cutter stamps out perfect donut rings and holes in a continuous, automated process. The cutting dies are precision machined from stainless steel to ensure sharp, clean cuts and minimal dough waste. Any scrap dough is immediately collected by conveyors and reintroduced into the mixing system for reuse. Each donut ring now travels along a conveyor to the second proofing chamber, essentially a gigantic, climate-controlled cabinet lined with slow-moving racks. Inside, the donuts undergo their final proof, where they double in size due to continued yeast activity. The environment here is tightly regulated, around 90 degrees here and nearly 85% humidity. This proofing process typically lasts 30 minutes, but sensors embedded in the chamber walls adjust for ambient shifts in temperature or humidity, ensuring each donut achieves the perfect rise. Now comes one of the most mesmerizing parts of the process, the fry line. The fully proofed donuts are gently deposited into a continuous flow fryer using an overhead lifting mechanism that preserves their delicate structure. The frying oil, usually a high-stability palm or soybean blend, is maintained at a precise temperature of approximately 365 degrees. Each donut floats along the surface, first frying one side, then automatically flipping at the midpoint using a mechanical turner. This results in the even golden brown exterior Krispy Kreme is known for, with a pale, proof line around the center indicating proper fermentation. The frying process takes just under a minute per side, and the timing is crucial. Over-frying results in a dense, oily product. Under-frying leaves it doughy and structurally unsound. Oil filtration systems continuously clean and circulate the frying oil, removing carbonized particles and extending the oil's life while maintaining food safety. Once the donuts exit the fryer, they move onto a draining conveyor where excess oil drips away. The donuts are now fully cooked, but they're still bare, until they pass through the glaze waterfall. This is the stage most visitors at Krispy Kreme stores eagerly watch through the viewing window. The glaze itself is a proprietary blend of confectioner's sugar, water, and stabilizers, mixed in large heated vats to maintain fluidity. It's heated to a precise temperature to ensure it flows evenly over the donuts without soaking them. As the donuts travel beneath the waterfall, a curtain of glaze coats their entire surface in one smooth motion. The donuts continue to move along the belt for several feet to allow the glaze to set. During this time, cooling fans blow across the surface to speed up the crystallization process, giving the glaze its characteristic sheen and snap. At this stage, the original glazed donuts are complete, but not all donuts stop here. Many are diverted down alternate lines for filling, topping, or decoration. Filled varieties like custard, jelly, or cream-filled donuts are processed using pneumatic injection stations. The donuts are gripped and punctured automatically, and then a precise quantity of filling is injected into each center using calibrated nozzles. Topping lines include various enrobing stations for chocolate dips, icing drizzles, and even cookie crumb coatings, depending on the product line. Once decorated, the donuts pass through a final quality control checkpoint. Here, high-speed cameras, sensors, and human inspectors work in tandem to identify deformities, glaze coverage issues, or structural flaws. Any donut that doesn't meet the company's stringent standards is diverted and discarded or sent for animal feed, depending on local regulations. Now comes the packaging process. Original glazed donuts are usually arranged by robotic arms into branded trays or boxes, depending on the sales channel, whether destined for in-store display, grocery retail, or food service distribution. Boxes are barcoded, date-stamped, and sealed automatically. For freshness, Krispy Kreme relies on just-in-time manufacturing. Many facilities bake and ship multiple times per day, with some outlets even co-located within the production plant itself to reduce handling and delay. For external distribution, the boxed donuts are loaded into climate-controlled trucks equipped with racking systems that prevent damage during transit. These trucks make scheduled routes to retail locations, grocery partners, and kiosk outlets, often arriving just hours after the donuts were made. Once on site, employees stock the shelves or display racks, ensuring the donuts are sold within their optimal freshness window, typically less than 24 hours. Meanwhile, any donuts not sold by the end of the day are generally removed to preserve Krispy Kreme's reputation for freshness. In some regions, unsold inventory is donated to food banks or repurposed, while others adhere to strict disposal policies. Throughout this entire process, automation and precision engineering play a central role. From programmable logic controllers managing the mixing and proofing cycles, to machine vision systems inspecting glaze coverage, every step is optimized for consistency, safety, and speed. The machinery involved is custom designed, often proprietary, and requires teams of trained technicians to maintain. Clean-in-place systems are installed throughout the facility to sanitize pipes, mixers, glaze troughs, and conveyors between production runs. This minimizes downtime while ensuring compliance with food safety regulations. Every aspect, from microbial swab testing to allergen control and traceability, is monitored via centralized software platforms, which can track each batch of donuts from flour silo to store shelf. The story of every M&M starts with one essential component: chocolate. The heart of a standard M&M is a solid drop of milk chocolate, though other varieties, like peanut, almond, crispy, pretzel, or peanut butter, feature different cores. But regardless of the variety, the production begins in the chocolate refining department, where raw ingredients such as cocoa liquor, cocoa butter, sugar, and milk solids are blended to make a smooth, consistent chocolate base. The chocolate used in M&Ms is tailored for firmness and melt resistance, specifically engineered to maintain its structure during the coating process. Large stainless steel tanks are used to melt and hold the chocolate at controlled temperatures. Automated valves and mixers regulate temperature, viscosity, and flow characteristics. Chocolate destined for M&M production must be carefully refined to reduce particle size, usually to around 20 microns. This is done in multiple stages using equipment like ball mills, roller refiners, and conchas. These machines apply friction, pressure, and shear force to break down the solid particles until the chocolate achieves its desired mouthfeel. Once refined, the chocolate is pumped to depositors, automated nozzles that precisely dispense the liquid chocolate into molds or droplet-forming equipment. For the classic M&Ms, the chocolate is dropped onto a cool, rotating belt in small, round portions, forming button-shaped discs. These droplets are cooled rapidly using chilled air tunnels to harden them before further processing. The cooled chocolate centers are then collected and sent to the coating drums. These are large, rotating pans, sometimes referred to as dragees pans or coating kettles, where the hard candy shell is gradually built around the chocolate core. This is the heart of the M&M production process and one of the most visually striking steps in the factory. The coating process is a slow and incremental buildup, achieved by spraying a fine mist of sugar syrup onto the tumbling chocolate centers, then drying and hardening that layer before repeating the cycle. Each coating drum can hold hundreds of thousands of chocolate centers at once. As the drum rotates, a fine spray of syrup, consisting mainly of sugar and water with optional corn syrup, is applied in short bursts. Warm air is then blown into the drum to dry the layer, allowing the sugar to crystallize into a thin, hard shell. This cycle is repeated dozens of times, each time adding a microscopically thin layer to build up the final shell thickness. Over time, this layering transforms the centers from soft chocolate buttons to perfectly round, hard-shelled candies. During this stage, technicians monitor coating uniformity, size consistency, and drying times using high-speed cameras and inline sensors. If the temperature or humidity in the coating room deviates too far from spec, it can ruin an entire batch, leading to shell cracking or poor adhesion. Once the desired shell thickness is achieved, the M&Ms are polished to give them their signature shine. This is done by adding polishing agents, such as carnauba wax or beeswax, to the coating drum in very small amounts. These natural food-grade waxes help create a glossy finish that not only enhances visual appeal, but also helps prevent sticking and moisture absorption during storage. The polishing phase takes less time than coating, but must be precisely timed to avoid overwaxing, which can result in a greasy or smeared appearance. The next step is color application, which may seem simple, but is, in fact, a carefully controlled phase. M&Ms come in a variety of colors, typically red, orange, yellow, green, blue, and brown. The color coding is applied using a sugar-based dye solution, sprayed in another round of layering inside rotating pans. Each batch is divided according to how many of each color are required. Food-grade colorants are mixed with water and a binding agent to ensure even adherence to the existing shell. After the colorant is applied, warm air is used to dry the layer, and another wax polish may be added to lock in the color and maintain shine. The factory uses precise batch tracking and automated scheduling software to ensure the correct number of each color is produced. For example, if red accounts for 20% of a standard bag's color distribution, the system ensures exactly that percentage is created during the run. This attention to detail keeps the consumer experience consistent across bags, boxes, and geographic regions. After color coding, the candies proceed to the printing station, where the iconic M is stamped on each piece. This is accomplished using high-speed, food-safe ink printers. The M&Ms are gently vibrated into a single layer on a moving conveyor belt that aligns them properly for stamping. The white edible ink is applied using a flexographic or offset stamping mechanism that imprints the M logo without damaging the candy surface. To ensure accuracy, machine vision systems monitor the printing in real time, checking for clarity, alignment, and completeness. Any candies that are misprinted or blank may be removed by pneumatic air jets and diverted for recycling or reprocessing. Now the M&Ms are ready for packaging. This phase of production involves a combination of robotics, weight-checking systems, and packaging machinery that operates at astonishing speeds. The candies are directed into vertical form-fill-seal machines or horizontal flow wrappers, depending on the packaging format. Multi-head weighers dispense precise quantities of M&Ms into each bag or pouch, ensuring weight compliance to legal standards. The packaging film is heat-sealed to form a tamper-evident, airtight barrier that preserves freshness and extends shelf life. For bulk formats, such as large tubs, party-sized bags, or vending packs, the process is slightly different but still highly automated. The machines are programmed to handle various product sizes, materials, and pack types without compromising accuracy. Barcodes, expiration dates, and lot numbers are printed onto each package to allow for traceability. Once packaged, the products are conveyed to case packing robots, which group them into cartons or boxes for shipping. These cases are then sealed, palletized by robotic arms, and shrink-wrapped for transport. Pallets are stored temporarily in climate-controlled warehouses before being loaded onto distribution trucks that carry them to retail centers, convenience stores, vending machine suppliers, and international shipping hubs. Throughout the entire process, food safety and quality control are paramount. The factory floor is governed by strict hygiene protocols. Employees are required to wear sanitary gear, and the equipment is sanitized regularly using automated clean-in-place systems. Random sampling is conducted at every critical control point, from chocolate refining to shell thickness to final packaging. Laboratory testing checks for microbial contamination, allergen presence, and chemical composition. Quality assurance teams also perform taste tests, structural integrity tests, and heat resistance trials to ensure the product meets Mars Inc.'s global standards. In the case of peanut or almond M&Ms, the process is similar but begins with nut preparation. Peanuts, for instance, are roasted in-house to develop their flavor and reduce microbial load. They are then cooled, sorted by size, and coated in a preliminary layer of chocolate before undergoing the same sugar shell layering process. Their irregular shape requires adjustments to coating speed and rotation patterns to ensure even coverage. The engineering behind M&M production is not only a marvel of food science, but also a study in high-speed manufacturing. Thousands of M&Ms can be produced every minute, yet each one must look and taste exactly the same. This requires the coordination of multiple disciplines: mechanical engineering, chemistry, automation, logistics, and sensory evaluation. The process begins not with whole potatoes, but with dehydrated potato flakes and potato starch. These form the base of the Pringles dough. The flakes are manufactured off-site through a separate drying process where peeled, cooked potatoes are mashed and then passed through drum dryers to remove water, creating thin, crisp sheets of dried potato. These are ground into fine granules and delivered to Pringles production facilities in bulk quantities, stored in climate-controlled silos to maintain moisture levels and prevent clumping. To this potato base, manufacturers add a precise blend of rice flour, corn flour, and wheat starch. This multi-starch formula gives Pringles their distinctive light, yet durable crunch, firmer than a classic chip, but less dense than a cracker. Each ingredient is selected for its functional properties. Rice flour contributes to lightness and reduces oil absorption. Corn flour provides structure and contributes to the crisp texture. Wheat starch acts as a binding agent and helps form the dough into a cohesive sheet. Inside the factory, these dry ingredients are metered into high-capacity industrial mixers. Water is added gradually, and the mixture is agitated until a cohesive dough forms. The consistency of the dough is critical. It must be pliable enough to be rolled and shaped, yet stiff enough to hold its form during frying. Too much water would cause the crisps to bubble and deform. Too little, and they would crack or crumble during processing. After mixing, the dough is conveyed onto a series of steel rollers in a sheeting machine. These rollers press the dough into a continuous, thin sheet, typically about 0.7 to 1 millimeter thick. The uniformity of this sheet is crucial, as even slight thickness variations can affect how the chips fry, blister, and brown. Advanced sensors mounted near the rollers continuously monitor sheet thickness, feeding data to the control system, which makes micro adjustments in real time. Next, the sheeted dough passes under a rotary die cutter. This is a cylindrical cutter with thousands of identically shaped molds engraved into its surface. As the sheet moves beneath it, the die cuts out dozens of curved oval crisps at a time, each one precisely measured to match Pringles' iconic dimensions, around 6.5 centimeters long and 5.5 centimeters wide, shaped with a unique double-curved profile known as a hyperbolic paraboloid. This mathematical shape isn't just aesthetic, it offers stackability, strength, and an audible crunch due to its uniform stress distribution. The dough scrap that remains between the cutouts is immediately separated and returned to the beginning of the process. Conveyor belts collect and transport the unused dough back to the mixer, where it is reincorporated into fresh dough. This closed-loop system minimizes waste and ensures efficiency in ingredient usage. Once cut, the raw crisps are gently lifted from the sheet using suction cups or air jets and placed onto a moving metal belt composed of dozens of concave molds. Each mold perfectly matches the chip's final saddle shape. This belt then moves the raw crisps into the fryer, an enormous stainless steel bath filled with hot vegetable oil, maintained at a consistent temperature of around 170 to 180 degrees. The crisps are submerged for approximately 11 seconds, long enough to remove moisture and induce a Maillard reaction, giving them their light golden brown hue and toasty flavor. Unlike traditional deep-fried potato slices that can curl, bend, or form bubbles, the Pringles molds maintain each crisp's structure during frying. Because the crisps are uniformly thin and precisely shaped, they fry evenly with no dark spots or oil saturation. Excess oil is quickly removed as the crisps exit the fryer and pass over a series of vibrating conveyors and air knives, high-pressure jets that blow away any surface oil or crumbs. At this point, the freshly fried crisps are hot, dry, and unseasoned. They move into the seasoning tunnel, a long, rotating drum equipped with sprinklers or spray nozzles. Here, flavor powders, ranging from classic original to sour cream and onion, cheddar cheese, or barbecue, are evenly applied as the crisps tumble and rotate. The flavor powders are formulated to stick to the crisp's surface via residual oil left from frying. In some varieties, additional ingredients such as powdered cheese or dehydrated vegetables are included in the seasoning blends. To prevent flavor loss and preserve freshness, the seasoned crisps are quickly cooled using forced air systems before entering the packaging phase. This cooling is critical. If the crisps are too warm, condensation can form inside the package, leading to soggy chips and microbial risk. Once cooled, they are conveyed to the stacking and canning line. This is where another defining feature of Pringles becomes prominent: their tubular canister. The stacking machine uses a system of synchronized mechanical arms, optical sensors, and robotic paddles to stack crisps one by one into perfectly aligned columns. This process is remarkably fast and precise. A sensor verifies each crisp's shape and orientation before it's inserted into the growing stack. Once a full stack reaches the correct height, typically around 80 to 100 crisps, depending on the packaging size, it is inserted vertically into a cardboard can that's been pre-formed and lined with a metallized film to prevent oil seepage and moisture intrusion. Each can is equipped with a plastic bottom, which is ultrasonically welded or heat sealed in place before filling. After the crisps are inserted, a foil lid is applied and hermetically sealed using induction heat or pressure bonding to ensure an airtight closure. A plastic snap-on cap is then placed on top, providing resealability for consumer convenience. The filled cans are then labeled and date-coded. Each can receives a printed batch number and expiration date to ensure traceability throughout the distribution chain. Vision inspection systems scan each can to ensure it is filled to the correct level, sealed properly, and free of any external defects like dents or mislabeling. Cans are grouped into multi-packs or cartons by robotic arms and placed on pallets for storage or shipment. Depending on demand and product line complexity, different varieties of Pringles may be produced in separate production runs on the same line, requiring quick and thorough cleanouts between batches to prevent flavor cross-contamination. From here, Pringles are shipped to distribution centers, retailers, and convenience stores across the globe. Thanks to the uniform shape and rigid packaging, they travel exceptionally well, with minimal breakage compared to traditional bagged chips. This durability, coupled with the brand's distinct identity, has made Pringles a staple in global snack markets. Sanitation and quality control are central throughout the process. Each stage of production, from dough mixing to final packaging, is monitored by automated control systems and human operators. Random samples are collected for lab analysis to check moisture levels, oil content, seasoning distribution, and texture. Microbial testing ensures no contamination occurs during handling. Metal detectors and X-ray machines inspect each can before shipping to catch any foreign objects that may have entered the line. Allergen controls are strictly enforced, particularly when switching between varieties like original and cheddar cheese. In addition to ensuring food safety, the factory design and equipment layout support continuous cleaning. Many machines feature clean-in-place systems that pump sanitizing fluids through the equipment without requiring disassembly. Air filtration systems and positive pressure rooms minimize the risk of dust and airborne contaminants affecting product quality. Beyond the manufacturing floor, the creation of new Pringles flavors and formats involves food scientists and R&D specialists who develop seasoning blends, test mouthfeel, and conduct sensory panels with trained tasters. Innovations like Pringles Wavy or Pringles Scorchin follow the same base process, with minor adjustments in dough formulation or seasoning protocols. Despite their high-tech origin, Pringles still deliver a simple satisfaction, a crisp, flavorful bite that feels familiar and fun. But behind that enjoyment is a complex dance of precision equipment, mathematical shaping, and carefully designed formulations. From powdered potatoes to perfectly stacked crisps, every Pringle is a product not just of flavor, but of industrial ingenuity, a testament to how food science can transform something as humble as a potato into a globally recognized snack. The process for Reese's peanut butter cups begins with the sourcing of high-quality raw peanuts, which form the core of the filling. These peanuts are typically sourced from farms in the southeastern United States, particularly Georgia, Alabama, and the Carolinas, where the climate and soil are ideal for peanut cultivation. Once harvested, the peanuts undergo initial cleaning, shelling, and sorting at the agricultural level before being shipped in bulk to the Reese's production facility. Quality control teams inspect every shipment, screening for mold, aflatoxins, and other contaminants. Peanuts are often tested for size, moisture content, and oil composition to ensure batch consistency. Upon arrival at the factory, the peanuts are conveyed to large storage silos. From here, the process of transforming raw peanuts into the signature Reese's filling begins. The peanuts are first roasted in large-scale industrial roasters, long horizontal drums heated by indirect gas-fired flames. These rotating drums tumble the peanuts slowly, ensuring even roasting. Temperature and humidity are closely monitored throughout the roast cycle, typically maintained around 320 degrees Celsius for about 30 to 40 minutes, depending on the peanut variety and moisture content. Once roasted, the peanuts are quickly cooled using forced air cooling tunnels to halt further cooking. The skins are then removed using a process known as blanching. In mechanical blanches, peanuts are agitated against rough surfaces or rubber belts that strip away the thin, papery skins. A series of air jets and vibrating sieves separate the skins from the now blanched nuts. At this point, the peanuts are ready to be ground. In most candy factories, this process takes place in two distinct phases. First, a coarse grind reduces the peanuts into a crumbly paste. Then, a finer grinding process, often using high-speed colloid mills or stone rollers, produces a smoother texture. However, unlike creamy commercial peanut butters designed for spreads, Reese's peanut butter filling maintains a slightly gritty texture on purpose. This signature mouthfeel is the result of limiting the duration of the fine grind and carefully controlling moisture levels. The ground peanuts are blended with additional ingredients, including sugar, dextrose, salt, hydrogenated vegetable oils, and sometimes a small amount of molasses or corn syrup solids. This mixture is prepared in large industrial mixing tanks equipped with powerful paddle agitators that ensure even incorporation. The blending process is closely monitored for temperature, viscosity, and particle size distribution, which directly affect the final texture and handling characteristics. The resulting peanut butter filling is slightly crumbly, yet cohesive, designed to hold its shape when formed, but melt smoothly in the mouth. While the peanut butter filling is being prepared, another part of the factory is busy tempering chocolate. Reese's peanut butter cups use a custom milk chocolate formulation that includes cocoa solids, cocoa butter, milk fat, sugar, lecithin, and vanillin. These ingredients are pre-blended and then passed through conching machines, large vats where granite rollers continuously knead the chocolate for hours at elevated temperatures. Conching improves texture and flavor by breaking down particles and promoting the development of complex chocolate notes. After conching, the chocolate is sent to tempering units, which precisely heat and cool the chocolate in a controlled sequence to encourage the formation of stable cocoa butter crystals. Proper tempering is critical to achieving that characteristic Reese's snap and glossy finish. The chocolate must be maintained at a working temperature of approximately 88 degrees to 90 degrees for milk chocolate, depending on the formulation. Now the production line shifts into high gear with the molding and filling of each peanut butter cup. The factory floor features a long assembly line comprising conveyor belts, servo-driven depositing heads, forming stations, and robotic arms, all synchronized with computer-controlled systems. First, paper cup liners are dispensed from reels and dropped into aluminum or plastic molds that give the peanut butter cup its distinctive ridged edge. These molds are carried forward on the conveyor to the chocolate depositing station. Here, a metered amount of tempered chocolate is deposited into each mold cavity, typically via piston-driven depositors with highly accurate flow control. The molds are then gently vibrated to level the chocolate and remove any trapped air bubbles. A specialized spinning or centrifugal molding mechanism is often used to coat the sides of each liner with chocolate, forming a thin shell that will encase the peanut butter filling. Once the bottom and sides of the shell are set, often using brief passes through cooling tunnels chilled to 40-degree if, the molds move to the filling station. At this point, the peanut butter mixture is slightly warmed to improve flowability and deposited into the center of the chocolate shell using a second set of depositors. The volume and placement are tightly controlled to ensure the filling does not breach the shell's perimeter, which would compromise product appearance and shelf life. The partially filled molds then travel through another cooling tunnel to partially firm up the filling before the final chocolate cap is added. At the next station, another measured deposit of tempered chocolate is layered on top to fully enclose the peanut butter. Vibratory and centrifugal actions again ensure that the top layer is smooth and fully seals the filling inside. After the top layer is applied, the molds pass through the final cooling tunnel. This tunnel, often more than 30 feet long, gradually lowers the product temperature to about 50 degrees to 60 degrees Fahrenheit, allowing the chocolate to fully crystallize and harden without cracking or bloom. At the end of the tunnel, robotic demolders invert the trays and the solidified Reese's peanut butter cups drop gently onto another conveyor belt, which carries them to the packaging line. Packaging is a critical part of the operation, both for aesthetics and product protection. Individual cups are wrapped in printed foil or plastic film using high-speed flow wrapping machines. These machines align, wrap, heat seal, and cut the packaging material in a continuous motion at speeds of hundreds of units per minute. Sensors and vision systems verify proper alignment, seal integrity, and date coding. Multiple wrapped cups are then grouped into standard pack formats, such as 2-packs, king size, or multi-packs, using pick-and-place robots that transfer the wrapped candies into cardboard sleeves or blister packs. These are then loaded into shipping cartons by automated case packers and sent through weight check stations and metal detectors for final safety assurance. Cartons are sealed, barcoded and palletized using robotic palletizers that arrange the boxes into stable stacks ready for shipment. The finished pallets are shrink-wrapped for transport and loaded onto refrigerated trucks if necessary, depending on the season and destination. Distribution centers receive the pallets and coordinate the movement of Reese's products to retail chains, vending machine operators, and wholesale clubs. Shelf life is generally around 6 to 9 months, and climate-controlled storage is crucial to preventing fat bloom or flavor degradation in the chocolate. Inventory is rotated using first-in, first-out logistics to ensure product freshness. Reese's peanut butter cups may seem like a simple treat, but their production involves a complex interplay of food science, automation, engineering, and quality control. Each cup reflects countless micro-adjustments made by operators, engineers, and sensors throughout the line to maintain consistency in taste, texture, and visual appeal. Whether you're biting into a miniature, a king size, or a seasonal shape, the same rigorous standards apply across every variation. The process for Snickers begins long before a single bar is formed. It starts with the procurement of raw ingredients, each of which must meet stringent quality, flavor, and food safety standards. The peanuts used in Snickers are typically sourced from large-scale growers in the United States, particularly Georgia, Texas, and Alabama, where soil composition and climate are well suited to peanut cultivation. Once harvested, the peanuts undergo shelling, drying, and initial quality control before arriving at the candy factory in bulk loads. At the receiving dock, they're sampled and inspected for size uniformity, absence of mold or aflatoxins, and overall freshness. The peanuts are then conveyed to roasting units, large, gas-fired, rotary drum roasters that tumble and cook the nuts evenly. Roasting time and temperature are carefully controlled, often in the range of 300 degrees to 330 degrees, to ensure the development of the characteristic deep nutty flavor and golden color. As the peanuts cool on vibratory trays with forced air, their skins are loosened and removed through mechanical blanching, which typically involves abrasion and suction systems. Once the peanuts are blanched, they are screened again for foreign matter or off-grade pieces before being held in stainless steel hoppers, ready for integration into the bar. While the peanuts are being prepared, another production stream begins with the making of the nougat layer, the foundational component of every Snickers bar. Nougat is a whipped mixture, typically composed of sugar, corn syrup, egg whites, and milk powder. The sugar and corn syrup are first combined in massive stainless steel cooking kettles, where they are heated to a precise temperature, usually around 240 degrees to 250 degrees, to achieve the correct sugar structure and viscosity. This hot syrup is then transferred to continuous mixing tanks, where it is combined with whipped egg whites and other dry ingredients. The blending process is highly aerated, giving the nougat its light, spongy texture. The finished nougat is deposited onto a moving conveyor belt lined with parchment or plastic film. It spreads out in a continuous sheet, generally about 1 to 2 inches thick. A series of levelers and rollers ensures uniform height and density across the sheet, which is then cooled slightly as it travels down the line. Once cooled and set, the nougat sheet proceeds to the caramel layering station. Caramel production occurs in its own dedicated section of the plant. A blend of glucose syrup, sucrose, dairy cream, and butter is cooked in open-jacketed kettles or vacuum cookers, where it is continuously stirred to avoid burning and to control the Maillard browning reactions that give caramel its signature flavor. The exact temperature and cooking duration are tightly monitored, typically between 240 degrees Celsius and 260 degrees. As soon as the desired consistency is achieved, firm enough to hold its shape but pliable enough to slice, it is poured or extruded onto the moving nougat sheet. The hot caramel forms a second, cohesive layer atop the nougat. To ensure perfect adhesion and uniform thickness, the bar sheet passes under heated rollers and through spreading nozzles that guide and adjust the caramel's distribution. The line is equipped with infrared sensors and weight check systems that continually monitor thickness and material ratios. Once the caramel has slightly cooled and stabilized, the bar sheet moves toward the peanut application zone. Roasted peanuts are sprinkled onto the warm caramel layer in a controlled shower using vibrating feed trays and metered dispensers. The combination of slightly sticky caramel and downward pressure ensures that most peanuts adhere securely. Excess or misaligned nuts are brushed away by rotating silicone paddles and collected for reuse or reprocessing. The peanuts used here are not only flavor critical, but also provide a distinctive crunch and texture contrast to the softer nougat and caramel. With all three internal layers assembled, nougat, caramel, and peanuts, the composite sheet now travels to the cutting area. Here, guillotine-style knives or rotary blade systems cut the long sheet into bar-length strips, typically around 1 inch wide. These strips are then cross-cut into individual bars using synchronized high-speed blades. Every bar is now a complete unit, except for the chocolate coating. Before coating, the uncoated bars, often referred to as centers, pass through a quick chilling tunnel to firm up the layers and maintain bar integrity during enrobing. Once firm, the centers are deposited onto a wide enrobing belt that passes through a chocolate waterfall. This enrobing process involves a curtain of tempered milk chocolate cascading down over the moving bars. As the bars move through the curtain, chocolate coats the top and sides. A bottoming plate or chocolate pool beneath the bars coats the underside as well. The chocolate used in Snickers bars is a proprietary blend of milk chocolate ingredients, cocoa butter, cocoa liquor, sugar, milk solids, and emulsifiers. The chocolate is pre-tempered in dedicated machines that heat and cool it through specific curves to ensure stable crystal formation. This tempering is what gives Snickers its glossy finish and prevents fat bloom during storage. The temperature of the chocolate is carefully maintained between 86 degrees Celsius and 90 degrees Celsius throughout the enrobing line. As the chocolate-coated bars exit the enrober, they pass under air jets and vibrating rods known as air knives and vibrators that remove excess chocolate, improve coating uniformity, and give each bar its final shape. The still warm chocolate is soft and easily deformed, so the bars immediately enter a cooling tunnel, which gradually reduces their temperature to around 50 degrees Celsius in a staged fashion. This gradual cooling prevents cracking and ensures that the chocolate shell sets with the correct texture. Once fully cooled, the bars emerge, ready for wrapping. A high-speed automated packaging line awaits, where each bar is individually wrapped using roll-fed film wrappers. These machines synchronize bar movement with film feeding, folding, sealing, and cutting, all in one continuous operation. Heat sealers close the film edges with precision, while inline printers apply best buy dates, lot numbers, and traceability codes. The wrapped bars are then conveyed to a grouping station. Depending on the market, Snickers bars may be packed individually, bundled in twin packs, or combined into multi-unit boxes. Robotic arms sort and orient the wrapped bars, placing them into cartons that are then sealed with hot melt adhesive. The packed cartons are passed through metal detectors and weight verifiers as a final check before palletization. Palletizing robots load the boxes onto standardized pallets, wrapping them tightly in plastic film for protection and stability during shipping. From there, pallets are staged in climate-controlled distribution centers. Temperature and humidity must be carefully controlled, especially in warm climates, to preserve the bar's texture and chocolate integrity. Snickers bars are then distributed to retailers, wholesalers, and vending machine operators worldwide. Shelf life for a standard Snickers bar is generally between 9 and 12 months, assuming proper storage. Mars maintains rigorous quality control protocols, including sampling every batch for flavor consistency, structural integrity, and microbiological safety. Automated inspection systems use vision technology to detect misaligned bars, incomplete coatings, or wrapper defects, automatically removing flawed units from the line. Throughout the plant, hygiene is paramount, with clean-in-place systems for all equipment and strict allergen controls to ensure product safety. What makes Snickers particularly remarkable is how such a complex, multi-layered treat can be produced with such uniformity at an industrial scale. From raw peanuts and liquid caramel to perfectly wrapped bars stacked on pallets, every aspect of production is optimized for speed, precision, and global distribution. Millions of Snickers bars roll off the line each day, each one representing a perfected system of mass food manufacturing. It all begins with cocoa beans for Hershey's chocolate, which are the fundamental raw ingredient in all chocolate. Hershey sources its cocoa beans primarily from West Africa, countries like Côte d'Ivoire and Ghana, where the climate, soil, and traditional farming practices produce high-yield crops with desirable flavor characteristics. Once harvested, the cocoa beans are fermented in banana leaf-lined piles and dried under the sun before being packed in jute bags and shipped across the ocean to Hershey's production facilities in the United States. Upon arrival, the beans are subject to rigorous testing. Random samples from each shipment are roasted and analyzed for aroma, acidity, moisture content, and potential contaminants. Approved beans are stored in large silos, sorted by origin and quality grade. From here, the first major step in the chocolate making process begins roasting. Roasting is not just about cooking the beans, it's a chemical transformation that unlocks the complex flavors hidden within the cocoa nibs. The beans are fed into large, rotating drum roasters or continuous belt roasters and exposed to carefully controlled dry heat at temperatures between 250 degrees and 300 degrees for 20 to 30 minutes. This Maillard reaction develops the chocolate flavor while drying the beans further and loosening the outer shells. The duration and temperature of the roast are adjusted depending on the origin and size of the beans, with constant airflow and humidity control. After roasting, the beans are cooled and sent through cracking machines that break them open, separating the brittle outer shells from the inner nibs. The broken shell pieces are removed through winnowing, a process that uses airflow to lift away the lighter shells, leaving behind clean cocoa nibs. These nibs are the essence of chocolate, rich in cocoa solids and cocoa butter. The nibs are then ground into a thick, gritty paste called chocolate liquor, not to be confused with alcohol. This step is performed in heavy-duty grinding mills, such as stone refiners or steel disc mills, which apply intense pressure and friction. As the nibs break down, their fat melts, turning the mass into a thick, flowing fluid. At this point, the chocolate liquor is still unrefined, with a coarse texture and bitter flavor. For milk chocolate, Hershey adds a blend of sugar, milk ingredients, and sometimes vanilla and lecithin to the chocolate liquor. One of the defining features of Hershey's milk chocolate is its use of fresh fluid milk that is processed in-house. Unlike European chocolates that often use powdered or condensed milk, Hershey pioneered a method of processing fresh milk into milk crumb, a dehydrated mixture of milk solids and sugar, using vacuum cooking and drum drying techniques. This milk crumb, with its slightly tangy cooked flavor, contributes to the uniquely Hershey taste. The chocolate liquor, milk crumb, and sugar are blended in large stainless steel mixing tanks, forming a uniform paste. At this stage, the mixture is still coarse and gritty, unsuitable for final chocolate texture. It must be refined. The refining process involves passing the chocolate mass through a series of roller mills, typically 5-roll refiners that reduce the particle size of the solids to less than 30 microns. The goal is to achieve a silky smooth mouthfeel without any noticeable graininess. Once refined, the chocolate enters the conching phase, one of the most critical steps in flavor development. Conching is a process of continuous mixing, aerating, and heating the chocolate over many hours to improve its taste and texture. Hershey's uses a combination of traditional longitudinal conches and modern rotary conches that knead the chocolate at controlled temperatures, typically between 120 degrees and 180 degrees. This process helps evaporate undesirable volatile acids, mellow bitter notes, and fully integrate the milk and cocoa flavors. The viscosity and aroma are fine-tuned during this stage through mechanical shearing and time adjustments. Following conching, the chocolate undergoes tempering, a heat treatment process that ensures the final product has a smooth, glossy finish and a crisp snap when broken. Cocoa butter can crystallize in several forms, but only one, known as Form 5, gives chocolate its ideal physical properties. Tempering involves heating the chocolate to about 115 degrees, then cooling it down to around 80 degrees, and finally reheating it slightly to about 88 degrees to promote the formation of stable crystals. This carefully controlled cycle is performed in continuous tempering machines, which maintain consistent temperatures and flow rates. Tempered chocolate is now ready for molding. Hershey's uses high-speed molding lines where liquid chocolate is deposited into polycarbonate molds in precise weights. The molds are vibrated to remove air bubbles and ensure even distribution. For classic bars like the Hershey's Milk Chocolate Bar, the molds are designed with the familiar rectangular break-apart sections embossed with the Hershey name. Once filled, the molds travel through long refrigerated cooling tunnels where the chocolate solidifies into its final form. As the bars cool, they are monitored by temperature sensors and mechanical feelers to ensure proper release. When fully set, the bars are automatically ejected from the molds and conveyed to the wrapping station. Modern wrapping equipment is synchronized with bar output and uses roll-fed film that is printed with the Hershey's branding, ingredients, and expiration codes. Wrappers are folded and sealed using rotary crimpers, and a barcode is applied for tracking. Wrapped bars are then grouped into cartons or display trays using robotic pick-and-place systems and conveyed to the end-of-line packaging area. Here, cases are formed, filled, and sealed before being palletized by automated arms. Each pallet is shrink-wrapped and scanned into inventory, ready for transport to distribution centers across the country and around the world. Throughout the entire process, quality control is a constant presence. Samples are pulled from every batch for testing. Sensory panels evaluate flavor and aroma, while lab technicians measure moisture content, fat percentage, and microbial levels. Machine vision systems inspect each bar for dimensional accuracy and surface defects. Metal detectors and X-ray machines scan for foreign objects, while thermal imaging cameras check for temperature compliance at various stages. Behind the scenes, Hershey's factories are tightly integrated with computerized control systems that track every ingredient, process parameter, and output metric in real time. From ingredient blending to chocolate tempering and bar wrapping, programmable logic controllers and supervisory control and data acquisition systems coordinate the hundreds of motors, valves, conveyors, and sensors that make up the line. These systems not only maximize efficiency and reduce downtime, but also ensure that each bar tastes the same as the one before it. Once packaged and palletized, Hershey's bars enter the post-production logistics chain. Distribution centers maintain climate-controlled storage to preserve chocolate integrity. Trucks are loaded according to first-in, first-out scheduling, and GPS tracking systems ensure timely delivery to retailers, vending machine operators, and wholesalers. Chocolate bars are especially sensitive to heat and humidity, so strict environmental controls are observed throughout transportation and warehousing to prevent melting or bloom. Interestingly, the Hershey flavor that many Americans recognize and even associate with nostalgia is not accidental. It's the result of deliberate formulation choices, particularly in how milk is treated during production. Some analysts believe the signature, slightly sour or tangy flavor found in Hershey's milk chocolate comes from the breakdown of milk fats into butyric acid during controlled lipolysis, an effect that differentiates Hershey's from creamier European chocolates. This flavor profile has become a cultural benchmark in the United States, deeply woven into American food identity. Despite decades of innovation and scaling up, the heart of Hershey's chocolate production still echoes the vision of its founder: to make high-quality milk chocolate affordable and accessible to everyone. With more than a century of history and tens of millions of bars produced annually, Hershey's remains a pioneer in automated food manufacturing, exemplifying the blend of tradition, precision engineering, and industrial food science. From bean to bar, the production of Hershey's chocolate is a story of transformation, driven by technology, but grounded in flavor. The manufacturing journey of Doritos begins long before the chips ever hit the fryer or the seasoning drums. It starts in the cornfields. Doritos use a specific variety of whole kernel yellow corn selected for its starch content, moisture levels, and particle uniformity after grinding. The corn is harvested at peak maturity and tested for aflatoxins, foreign material, and protein content before it's even accepted at the plant. Only corn that passes this first round of quality standards is brought in for processing. At the factory, truckloads of bulk corn arrive daily and are funneled into underground receiving pits that use gravity to guide the kernels onto conveyor belts. These conveyors feed the kernels into the first stage of preparation, the cleaning and sorting system. In this system, the corn passes through an array of vibrating sieves, rotating drum sifters, and powerful pneumatic air classifiers. Large debris like cobs, sticks, or stones are removed first. Then, finer contaminants like dust and small broken kernels are extracted using aspirators that draw away lightweight particles. Magnetized rollers also scan the corn flow to remove any traces of ferrous metal, ensuring total cleanliness before cooking. Once cleaned, the corn moves into the nixtamalization phase, a crucial and traditional process that transforms the flavor, texture, and nutritional properties of the corn. Nixtamalization involves cooking the whole kernels in a large stainless steel vat of hot water mixed with food-grade calcium hydroxide, also known as slaked lime. The corn is cooked at around 85 to 90 degrees Celsius for approximately 20 to 40 minutes, depending on the batch size and corn variety. This lime water solution serves several purposes. It breaks down the outer pericarp of the kernel, making it easier to grind and digest. It also increases the bioavailability of niacin, softens the internal structure of the corn, and imparts the distinctive flavor profile that Doritos are known for. After cooking, the corn is not immediately processed but left to soak, usually for 8 to 12 hours in the same solution. This extended soaking allows the lime to fully penetrate the kernel and continues the softening and flavor-enhancing process. After the soaking phase, the corn is drained and rinsed thoroughly in large industrial washers that spray it with jets of clean water while gently tumbling the kernels. The goal is to remove the loosened pericarp, excess lime, and any residual cooking liquid. What remains is called nixtamal, a soft, pliable corn mass that still holds the shape of whole kernels, but has a meaty, hydrated texture. The nixtamal is now ready to be ground into masa, the dough-like base of every Dorito chip. The grinding is performed using industrial stone mills, rotating horizontal stones made of volcanic rock or synthetic composites, precisely aligned to maintain a consistent grind size. The nixtamal is fed between the stones, and the pressure shears the softened corn into a dense, cohesive paste. This paste is the masa, and its texture is critical. It needs to be soft enough to press, but dry enough to hold shape without sticking. Operators continuously monitor the temperature of the mesa during grinding. Too much friction can overheat the dough, which affects the final chip texture. Ideal mesa temperature coming off the stones is around 45 to 55 degrees Celsius. Viscosity is checked using inline sensors that measure flow resistance, and if adjustments are needed, small amounts of water or returned dry mesa are mixed back in using an automated feedback loop. Now, it's time to form the masa into flat sheets. The ground mesa is transported via auger screws into a sheeting machine, which extrudes the dough between two polished stainless steel rollers. These rollers are adjustable to control sheet thickness down to the millimeter, usually targeting between 1.2 and 1.8 mm, depending on the final chip specification. The mesa sheets are laid directly onto a continuously moving conveyor belt that carries them to the cutting station. The cutting system is a rotary die cutter, a high-speed drum outfitted with rows of equidistant triangular blades, each perfectly matched to the iconic Doritos shape. As the mesa sheet moves beneath the drum, the rotating blades stamp out thousands of identical triangle chips per minute. Each cut is sharp and precise, with just enough spacing to leave minimal waste dough between cuts. The trimmings, the thin slivers of masa between triangles, are not discarded. They are automatically lifted via vacuum collection and returned to the start of the sheeting process. These scraps are reincorporated into the fresh dough, ensuring efficient use of material and maintaining consistency. The cut triangle chips now move on a flat conveyor to a brief baking phase, which we'll explore in detail in the next section. This preliminary baking is vital to reduce moisture and stabilize the chip before it enters the high heat frying zone. But before any oil is introduced or seasonings are applied, this early stage, cleaning, nixtamalization, grinding, sheeting, and cutting, is where the foundation of Doritos' crunch, shape, and flavor truly begins. Once the precisely cut mesa triangles are formed and conveyed forward, they reach one of the most critical transitions in the Doritos factory, the pre-baking zone. Though often overlooked, this short but essential phase serves as a structural stabilizer that prepares each chip for frying without deforming, bubbling uncontrollably, or becoming overly saturated with oil. This stage controls the internal moisture content and builds the texture foundation that will result in the signature crunch. The masa triangles, still soft and slightly tacky from the sheeting process, move onto a continuous metal mesh conveyor belt that leads directly into an industrial tunnel oven. This pre-bake oven is not designed to fully cook or brown the chip. Instead, its primary goal is to reduce the moisture level from roughly 50% down to about 25 to 30%. This ensures the surface of the chip becomes firm enough to hold its shape when exposed to hot oil, but not so dry that it resists expansion. The oven itself is typically divided into multiple thermal zones. The first zone begins around 160 degrees Celsius, gradually increasing to about 260 degrees Celsius by the final section. Heated air is circulated by high-velocity blowers, creating a turbulent flow across the top and bottom of the chips to ensure uniform dehydration. The baking conveyor is made of stainless steel mesh that allows hot air to penetrate from below, guaranteeing that no side of the chip is undercooked. Sensors monitor humidity at various checkpoints, and real-time data is fed into the oven's PLC system to dynamically adjust airspeed and temperature depending on fluctuations in mesa density, ambient humidity, or line speed. As the chips exit the oven, they emerge firmer, drier, and more resilient, yet still pale in color and lacking the blistered surface texture that defines a finished Dorito. That transformation happens in the next stage, the continuous fryer system. Here, the par-baked chips fall gently off the oven belt and descend onto the infeed section of a massive open-surface fryer. The fryer itself is a high-capacity stainless steel vessel filled with continuously filtered cooking oil. Most Doritos production lines use either corn oil, sunflower oil, or a proprietary blend of vegetable oils chosen for their high smoke points and neutral flavor profiles. The oil is maintained at a stable frying temperature of approximately 180 degrees Celsius, with variations of only plus 2 GC allowed during operation. Chips are submerged in the oil for about 35 to 55 seconds, depending on their exact moisture level and thickness. The chips ride through the fryer on a submersion conveyor, essentially a mesh belt with downward pressure bars that keep the chips fully immersed while preventing stacking or overlap. This is crucial because the frying process is not just about dehydration, it's about vaporization. As the residual water inside each chip turns to steam, it forces itself outward, puffing the chip slightly and creating those micro blisters and bubbly textures on the surface. This internal steam pressure is carefully managed. Too little and the chip stays flat and hard. Too much and it balloons into a hollow pocket. Above the fryer, exhaust hoods pull away steam and vaporized oil particles, filtering them through a heat recovery system that can reuse waste heat to pre-warm incoming oil. This system conserves energy and helps maintain a cleaner frying environment. The oil itself is constantly recirculated through centrifugal filters and fine mesh screens to remove crumbs, starch residues, or burnt particles. Fresh oil is added in controlled volumes throughout the day to maintain chemical balance and replenish lost volume. Once fried to the optimal light, golden color, the chips are lifted from the oil by an outfeed conveyor and immediately pass through a vertical de-oiling section. Here, powerful centrifugal blowers aimed at precise angles blast away excess surface oil. This keeps the chips crispy, prevents pooling in the packaging stage, and ensures that the seasoning will stick without creating grease buildup. The chips then pass through an ambient cooling tunnel to bring them quickly down to room temperature. Cooling is not merely for worker safety, it stabilizes the fat within the chip and prevents condensation when entering the seasoning drums. Now comes one of the most defining stages of the entire process: seasoning application. Each Dorito must carry the bold, vibrant flavor profile it's known for, whether that's nacho cheese, Cool Ranch, spicy sweet chili, or any of the dozens of global variants. The seasoning powder itself is a proprietary blend of flavorings, including real cheese powders, spices, salt, sugar, yeast extract, and encapsulated flavor oils that deliver controlled release bursts of taste. The chips are conveyed into a rotating seasoning drum, an inclined, slowly turning cylinder lined with food-grade stainless steel. As the chips tumble over one another, a dry powder dosing system mounted above the drum applies the seasoning using precision augers and dispersing nozzles. These nozzles can spray a uniform mist of oil if needed before the seasoning hits, which enhances adhesion for certain formulations. The rotation speed of the drum, the flow rate of the powder, and the incline of the system are all adjustable and carefully tuned. Too slow, and the powder won't distribute evenly. Too fast, and the chips may break, or the powder may collect unevenly on some sides. Optical sensors track the color and surface reflectivity of the chips as they exit the drum. If the reflectivity is too high, that could indicate under-seasoning. If it drops below a preset threshold, over-seasoning may be occurring. This live data is fed back into the controller, which tweaks the feed auger speed or pauses the oil spray accordingly. The seasoning drum is one of the most customized parts of the Doritos line. Different flavors use different particle sizes, densities, and oil volumes, which means the drum design and spray system must adapt depending on the product. Some drums include vibrating baffles or spiral lifts that increase tumbling action for extra thick chips or extra coarse seasoning. Once seasoned, the chips are directed into the weighing and bagging system, but before that, they undergo an automated inspection phase. High-speed vision cameras scan every chip for size, shape, and color. Broken chips, overly curled pieces, or visibly under-seasoned chips are removed via air-jet rejectors. These rejected chips are collected and sent either for regrinding or biomass energy use. Only chips that pass inspection enter the multi-head weighers, machines equipped with a dozen or more radial weighing hoppers. These hoppers constantly drop chips into a central collection bucket when the combined weight equals the target for each bag, typically between 28g and 198g, depending on package size. Once a precise combination is reached, the chips are dropped into a vertical form-fill-seal bagging machine. Here, continuous rolls of metallized polypropylene film are formed into tubes, sealed along the sides, and crimped at the bottom. The weighed chips are dropped into the formed bag tube just before the top is sealed and cut. Each bag is nitrogen flushed to displace oxygen, extending the product's shelf life and preserving crunch. Then, the bags are labeled, batch coded, and pass through a final metal detector before being boxed for palletization. After the freshly seasoned Doritos chips are individually weighed, bagged, sealed, and inspected, the production line moves into the critical post-packaging and logistics phase, where efficiency and traceability become as important as taste and texture. Though the chips are now fully formed and flavor complete, the operation is far from over. In fact, from a manufacturing systems perspective, the next stages, palletization, storage, shipping, and quality verification, are just as sophisticated and optimized as any in the earlier production line. The newly filled Doritos bags exit the form-fill-seal machines onto a series of conveyor belts designed to collect, orient, and organize them by SKU, bag size, and flavor variant. These conveyor lines merge into case packing stations, which use robotic arms equipped with vacuum suction grippers or gentle mechanical paddles to lift and place the chip bags into cardboard cartons. These boxes are pre-folded, glued, and printed with relevant product information, including product code, flavor, best before date, factory location, and a scannable QR or barcode that links to all production details. Each carton is inspected for weight and shape before it moves to the next phase. Even slight deviations in shape, caused by mispacked bags or an uneven number of chips, can disrupt downstream palletizing operations, so edge integrity and sealing quality are monitored automatically using high-resolution 3D scanning systems. Any carton that fails to meet dimensional tolerance is rejected from the main flow and rerouted for manual inspection or reboxing. Once cleared, the filled cartons are transferred to automated palletizing stations. In most modern Doritos factories, this process is entirely robotic. A multi-axis robotic arm lifts groups of cartons and stacks them onto wooden or composite pallets according to a predefined stacking pattern optimized for shipping efficiency and stability. These patterns are determined by a logistics algorithm that accounts for box dimensions, weight distribution, and the pallet's ultimate destination, whether that's a domestic warehouse or a long-haul overseas container. After each pallet is completed, a robotic stretch wrapper encircles it with several layers of clear plastic film to stabilize the load. A printed pallet ID label is affixed, containing detailed information about its contents, including product types, quantities, batch numbers, and destination. These labels are scanned into the warehouse management system, linking each pallet to the larger production database in real time. From here, pallets are routed into the warehouse zone. Doritos production facilities feature climate-controlled warehouses designed to maintain product quality throughout the storage period before distribution. These zones are not refrigerated, as Doritos are shelf-stable, but they are meticulously managed to avoid conditions that could lead to staleness or packaging deformation. Temperatures are generally held between 18-22 degrees Celsius, and humidity is controlled below 50% to prevent foil bags from absorbing moisture or warping. Inventory in the warehouse is managed by automated storage and retrieval systems. Tall racking structures are navigated by robotic cranes that pick and place pallets based on real-time demand, stock rotation policies, and shipping schedules. Each pallet's position in the warehouse is logged down to the specific shelf and column level, making retrieval highly efficient. The warehouse management system is integrated with the factory's enterprise resource planning software, ensuring that production and distribution are fully synchronized. While in storage, every pallet of Doritos is subject to randomized quality control sampling. A team of trained technicians removes sample bags from various pallets across shifts and production lines and sends them to a separate sensory evaluation lab within the facility. Here, samples undergo a series of tests: mechanical compression for bag integrity, gas analysis for nitrogen content, and oxygen intrusion, seasoning density checks, and most importantly, taste and crunch testing. Crunch is measured using a texture analyzer, a machine that applies controlled force to the chip and records resistance, fracture point, and acoustic feedback. The results are compared to golden standard reference chips to determine if the texture profile remains within acceptable limits. Seasoning adhesion and intensity are tested via flavor profile mapping, and every element from saltiness to umami to residual aftertaste is scored and compared against target values. If a trend of inconsistency is detected, an investigation is initiated, often leading to a review of upstream production parameters like fry temperature variability, seasoning drum throughput, or even ingredient batch variations. This closed-loop system helps prevent long-term quality drift and enables real-time course correction. Beyond the factory, the logistics infrastructure that gets Doritos from warehouse to retail shelves is another marvel of scale and precision. The factory works in tandem with PepsiCo's broader distribution network, which includes regional distribution centers, cross-dock terminals, and last-mile delivery nodes. Based on retail demand forecasts drawn from sales data, seasonal trends, and real-time POS metrics, shipment volumes are adjusted dynamically. This avoids overproduction and waste while ensuring retailers remain stocked. Each shipment of Doritos is accompanied by a digital bill of materials, which includes all traceability data from ingredient sourcing to packaging and palletization. This document allows not only for internal tracking, but also rapid action in the event of any product recall or customer complaint. If an issue is raised about a particular bag, say under-seasoning in a certain region, operators can trace the issue back to a specific lot, machine, shift, and even the original corn batch used in production. Globally, the manufacturing process for Doritos is also adapted based on regional consumer preferences and regulatory standards. While the foundational steps remain consistent, nixtamalization, sheeting, cutting, frying, and seasoning, the recipes and specifications can vary significantly. For example, in the US, cheese-based seasonings often use cheddar powder and lactic acid for tang, while in the UK or India, formulations may include less salt or alternative flavor enhancers to meet local guidelines or taste expectations. In markets like Japan or South Korea, where flavor sophistication and novelty are highly valued, factories produce limited edition Doritos featuring ingredients like wasabi, squid ink, or yuzu citrus. These variations often require changes in seasoning particle size, oil stability, or packaging material, and as such, the production lines must remain flexible. To facilitate this, Doritos factories use modular flavor dosing systems and quick changeover machines that allow seamless transitions between variants with minimal downtime. In addition to this flexibility, Doritos production lines are increasingly being outfitted with smart factory technologies. These include IoT sensors, predictive maintenance platforms, and AI-driven scheduling software. For instance, a vibration sensor might detect a subtle change in the seasoning drum's motor function that suggests a bearing is beginning to fail. Rather than waiting for a breakdown, the system automatically schedules maintenance during a planned production lull, avoiding unplanned downtime. Energy efficiency is also a growing focus. Waste heat from the fryers is often recovered through heat exchangers and used to preheat water for the nixtamalization tanks or warm the air in the seasoning room. Air filtration systems recycle hot air from the fryer exhaust into the building's HVAC to reduce natural gas usage. These sustainability practices help reduce both costs and environmental impact. Waste reduction is another area of innovation. Trimmings from mesa sheeting, broken chips, and seasoning dust are no longer treated as loss. Instead, they're collected, analyzed, and often reused in animal feed production, compost systems, or converted into biofuel at third-party processing facilities. Factory waste targets are set annually, and each production shift is scored on both yield efficiency and environmental impact. Ultimately, the journey of a Dorito from corn kernel to crunchy triangle is one of constant refinement. At every stage, whether it's dough hydration, fryer calibration, seasoning density, or robotic case packing, the process is governed by a matrix of mechanical precision and human sensory experience. The chips may seem simple to the average consumer, but behind every bag lies a production system that blends food science, industrial engineering, supply chain logistics, and consumer psychology into one unmistakable result: bold flavor, addictive crunch, and global brand consistency. It all starts with the Consumer Insight Team, which continuously analyzes sales data, social media trends, cultural food movements, and even fine dining innovation to identify gaps or opportunities in the market. A spike in interest around birria tacos, for example, might inspire a spicy beef consomme Doritos concept. Once a viable trend is spotted, food scientists and flavor chemists work alongside marketing strategists to develop flavor direction briefs, detailed documents that outline the intended taste profile, emotional positioning, and target audience. In PepsiCo's Flavor Innovation Centers, teams begin with flavor mapping. This involves breaking down target flavors into their basic aromatic and taste components. For a concept like Flamin' Hot Dill Pickle, the scientists would analyze heat components, acidity, herbal notes, and salt balance. Using GCMS, flavor chemists extract and replicate aromatic profiles to ensure they match real-life foods as closely as possible. Next, benchtop seasoning blends are created in small batches using food-grade flavor powders, encapsulated oils, anti-caking agents, and natural extracts. These are applied to test chips using miniature tumblers that mimic the behavior of full-scale seasoning drums. Each test batch is evaluated by sensory panels, trained tasters who assess flavor intensity, balance, aftertaste, aroma, and how the flavor interacts with the chip's natural corn and oil base. Their feedback is mapped against a flavor wheel to identify gaps or off notes that require reformulation. Multiple iterations are often needed. Some spices may clump, certain acids might degrade in heat, and some flavor oils could lose their punch after just a few days in packaging. Stabilizers and carriers are used to protect volatile components, and microencapsulation techniques ensure that heat-sensitive ingredients only release during mastication, not while sitting in the bag. Once the flavor passes internal panels, the next phase is consumer testing. In select cities, Doritos organizes blind taste tests, sometimes with up to 500 participants per flavor. Reactions are scored not only on flavor, but on memorability, uniqueness, and potential repeat purchase behavior. Statistical modeling software crunches this data to identify the most promising formulas. When a flavor is approved, it must be scaled up to factory levels without losing its integrity. Seasoning blends are manufactured in industrial blenders, often in batches of hundreds of kilograms. The bulk seasoning is tested for particle size, uniformity, moisture absorption, and flow behavior. During this phase, the seasoning is often reformulated slightly for stability, color consistency, and performance under high-speed drum tumbling. Then come the pilot runs. A limited quantity of chips is produced on a full-scale Doritos line using the new flavor. This lets engineers monitor how the seasoning behaves under actual production conditions, how well it sticks to the chip, whether it builds up on machinery, how the oil in the powder affects packaging line sensors. If issues arise, tweaks are made not just to the formula, but to the machinery settings as well. Finally, once all checks are passed, the new flavor enters full production, often accompanied by bold marketing campaigns and timed releases. Global coordination ensures that ingredients meet regional compliance, and new flavors often debut in test markets before rolling out broadly. These launches are tracked in real time, and consumer response loops back into the development pipeline, influencing which flavors stay, evolve, or disappear. This highly coordinated, scientific, and iterative approach allows Doritos to launch daring new flavors while maintaining the consistency and production efficiency that a global brand demands. Each new taste starts with creativity, but ends in finely tuned, factory-scale execution. Unlike traditional potato chips, which are sliced from whole potatoes and deep fried, Pringles begin life in the form of a dough. That's right, each Pringle is crafted from a carefully developed dough made from dehydrated potato flakes, corn flour, rice flour, and a precise mix of emulsifiers, oils, salt, and flavorings. This composition is no accident. It's designed for processability, uniformity, and that distinctive light, crispy crunch. The journey begins with sourcing and preparing the raw ingredients. Dehydrated potato flakes, the primary ingredient, are supplied by potato processing plants that convert whole potatoes into a dry, shelf-stable form. These flakes are produced by washing, peeling, cooking, mashing, and finally drying the potatoes into flakes through a drum drying or belt drying process. The quality of these flakes is critical. They must have consistent moisture, starch, and texture characteristics to behave predictably in the Pringles dough. In the factory's raw materials storage area, huge silos hold the potato flakes, as well as corn flour and rice flour. These are conveyed through enclosed pneumatic systems into high-capacity ingredient blending hoppers, where each component is dosed with incredible accuracy. Every batch of dough requires precision, down to the gram, to ensure the final product maintains the correct structural properties, color, and flavor balance. Ingredients are mixed in a horizontal ribbon blender or paddle mixer, often in batches of several hundred kilograms at a time. Water is then added gradually to the dry mix, and the entire mass is blended under tightly controlled conditions to form a malleable, uniform dough. The water temperature, mixing time, and total moisture level are all carefully monitored by PLC-controlled systems. The dough must be neither too dry, resulting in cracking during forming, nor too wet, which would lead to expansion or puffing during frying. Instead, the goal is a smooth, pliable dough with a clay-like consistency that can be shaped, cut, and fried without distortion. Once the dough is ready, it's transferred via conveyor to the sheeting line. This is where the process becomes highly visual and mechanical. The dough enters a series of rotating rollers, which press it into a continuous thin sheet, about 1 to 2 millimeters thick. These rollers apply uniform pressure across the width of the belt, creating a dough sheet that is even in thickness from edge to edge. Sensors above the belt continuously scan the sheet for thickness deviations, triggering automatic adjustments if needed. Next, the dough sheet passes under a rotary cutter, a drum outfitted with precision-engineered dies in the shape of the iconic Pringle oval. As the cutter rolls over the moving dough sheet, it cuts out uniform ovals, which are gently lifted off the belt using a vacuum system or pickup fingers and placed onto metal cooking molds. These molds are slightly concave to give the chip its characteristic hyperbolic paraboloid shape, often referred to as a saddle curve. Any leftover dough between the cutouts is collected by scrapers, rehydrated, and recycled back into the mixing process. This near zero waste approach is one of the key efficiencies of the Pringles process. It's also one reason the chips are so uniform. Every piece of dough goes through the same treatment again and again until it reaches the fryer. Once placed on the curved molds, the uncooked Pringles move via conveyor into the continuous fryer. This piece of equipment is massive, often stretching 10 to 15 meters in length, and filled with high-stability cooking oil, usually sunflower or corn oil, heated to around 180 degrees to 190 degrees. As the metal trays holding the chips travel through the fryer, the dough crisps into its final form. Each chip is fried for a precise duration, usually between 10 and 20 seconds, to ensure it emerges golden, crispy, and with the exact moisture content required for long shelf life and a satisfying snap. Because the chips are held in molds during frying, they maintain their consistent curve and do not puff or fold. This gives them the clean, stackable quality that defines the brand. The oil used in the fryer is continuously filtered and topped up to maintain purity and minimize off flavors. Inline sensors monitor the oil temperature, flow rate, and chip throughput to keep the process optimized at all times. After frying, the chips pass through an oil drain section, often assisted by compressed air jets or vibrating conveyors that shake off excess oil. The chips are then conveyed to a cooling system, a multi-stage area where fans and ambient air bring the chip temperature down quickly but gently. Proper cooling is essential before flavor application. Too much heat and the flavor powders will degrade or fail to adhere properly. Once cooled, the Pringles are directed into the seasoning tumbler. This is a large, rotating stainless steel drum where chips are gently tumbled while dry flavoring powders are sprayed or sifted onto their surfaces. A light mist of oil may be reapplied before this step to help the powders stick. Seasoning can include classic salted flavors, sour cream and onion, barbecue, cheddar, or custom blends formulated in-house by flavor scientists. Each seasoning blend is composed of salt, acids, cheese powders, natural and artificial flavors, and sometimes even encapsulated aromas that release in the mouth. As the chips roll through the seasoning drum, every surface is coated evenly thanks to the drum's speed, angle, and baffle design, which keeps the product moving in a gentle, randomized pattern. The process is engineered so that not only is flavor distribution even, but breakage is kept to an absolute minimum. After all, uniformity is part of what makes a Pringle a Pringle. Once flavored, the chips proceed to the stacking station, a marvel of mechanical choreography. Conveyor belts equipped with sensors and robotic arms gently align the Pringles into neat vertical stacks, each containing an exact number of chips per tube. As the stacks are formed, they are transferred onto a platform that slides them into waiting Pringles cans, the brand's signature packaging that also serves as a structural support, keeping the delicate chips safe from breakage. As the neatly formed stacks of Pringles are guided toward the packaging area, we enter one of the most unique elements of the brand's manufacturing process: the creation and loading of the Pringles canister. Unlike traditional snack foods that use pillow bags or plastic trays, Pringles uses a rigid composite can designed to protect the delicate stacked chips from breakage and to maintain freshness for extended periods. The Pringles canister is a marvel of engineered packaging. It's made of composite cardboard wound into a cylinder with a metal foil-lined bottom and a plastic snap-on lid. Each element of the can is optimized for shelf life, stacking strength and brand identity. The inner lining of the can is coated with a thin layer of aluminum foil or a moisture-resistant laminate that acts as a barrier against humidity and oxygen, two of the biggest enemies of fried snack foods. The exterior, of course, is wrapped in a colorful printed label indicating the flavor, nutritional information, and branding. In the packaging area of the factory, canisters are assembled and formed on-site or delivered pre-formed, depending on production volume and facility layout. High-speed rotary machines apply the foil bottoms to each cardboard tube using a heat or adhesive sealing process. Once the bases are sealed, the empty cans are conveyed toward the chip stacking zone, where robotic systems are already preparing the next batch of perfectly formed chip stacks. With the chips cooled, seasoned, and stacked into uniform columns, a synchronized pusher arm aligns with the moving conveyor and gently nudges each stack into the open can. This is done with remarkable precision. Too much force and the chips will crack or compress. Too little and the stack may tip or shift inside the can. Every stack is composed of a standard number of chips, most often between 80 and 100, depending on flavor, region, and package size. Weight sensors downstream confirm each can's fill weight to verify proper loading. Next, each filled can passes through a nitrogen flushing station. This is a vital step in the preservation process. Before the plastic lid is applied, a short blast of food-grade nitrogen gas is injected into the can to displace any oxygen. Nitrogen is inert and doesn't react with fats or seasonings, making it ideal for extending the shelf life of fried foods. By eliminating oxygen, this step slows down oxidative rancidity, preserving the taste, aroma, and crunch of the chips for several months. Immediately after flushing, the snap-on plastic lid is applied. These lids are manufactured from injection-molded polypropylene or polyethylene and are flexible enough to form a tight seal without adhesives. In some cases, a foil pull tab seal is applied just below the lid for additional freshness protection or tamper evidence, especially for export markets or special edition products. Once sealed, the cans are rotated and conveyed through label verification systems, where barcode scanners and cameras inspect each label for alignment, print clarity, and proper coding. Date codes, production line identifiers, and batch numbers are printed on the can's bottom using high-speed inkjet or laser printers. These codes are crucial for traceability in the event of a recall, complaint, or audit. From here, the sealed Pringles cans are grouped into secondary packaging formats. Depending on the market and distribution requirements, this could include shrink-wrapped multi-packs, shelf-ready trays, or corrugated cartons. Robotic arms equipped with suction cups or pneumatic grippers stack cans horizontally or vertically into their assigned configurations. These groups are then passed through a heat tunnel to shrink-wrap them into a durable bundle, or they are placed directly into cartons for larger shipments. At this point, each grouping is staged for palletization. Robotic palletizers pick up completed cases and organize them into layered patterns optimized for space and stability. Each layer of cases is carefully aligned to minimize shifting during transportation. Once the pallet is fully loaded, it is automatically wrapped in stretch film and labeled with a unique shipping ID. This barcode ties the pallet to a digital inventory management system that knows its contents, weight, destination, and production timestamp. Before any pallet leaves the factory floor, strict quality control protocols are enforced. At multiple stages along the line, from dough mixing to packaging, line workers and QA technicians pull random samples for analysis. These samples are tested for moisture content using gravimetric or infrared drying methods, oil content using Soxhlet extraction or near-infrared analysis, color using colorimeters calibrated to Pringles' specific golden hue, breakage percentage by simulating drop and vibration tests, flavor uniformity through sensory panel evaluations conducted in specialized tasting booths. Each facility maintains a detailed product specification profile for every flavor. If any attribute, texture, taste, size, weight, falls outside these boundaries, corrective actions are triggered. This might include rebalancing the dough mix, adjusting fryer dwell time, recalibrating seasoning dispensers, or reprogramming stacking arms. In rare cases, product may be quarantined and destroyed if it fails microbiological or allergen controls. In parallel with physical testing, real-time data monitoring systems are constantly logging hundreds of variables across the plant. These include fryer oil, turnover rate, seasoning application rates, cooling tunnel temperatures, nitrogen pressure, and wrapping line speed. Plant operators access these through human-machine interface terminals, which are integrated with supervisory control and data acquisition systems. These tools allow live oversight of every critical process and make troubleshooting faster, smarter, and more proactive. Food safety is paramount throughout the entire operation. The plant is designed around zoning principles to minimize cross-contamination, meaning that raw ingredients, in-process dough, cooked product, and finished goods all move through different hygienic areas. Airflow systems, sanitation teams, and stainless steel equipment ensure compliance with GFSI, FDA, and ISO 20000 standards. Allergen controls, cleaning schedules, and traceability systems are regularly audited by third-party certification bodies. Meanwhile, sanitation and efficiency go hand in hand. After each production run or flavor change, the line undergoes a full clean-in-place procedure. Dough mixing vessels are flushed, sheeters and cutters are wiped down, seasoning drums are vacuumed, and oil is filtered or replaced. All maintenance events are logged digitally, and any anomalies in cleaning schedules are flagged for review. In terms of sustainability, the Pringles production system has also evolved. Cooking oil is now often recycled and re-refined after filtering. Off-spec product, chips that are broken, underfried, or misflavored, are collected and ground into animal feed or converted to energy through anaerobic digestion. Waste heat from fryers is repurposed to preheat incoming processed water. Even packaging waste from trimming labels or misprinted cartons is collected, baled, and sent to specialized recyclers. But sustainability doesn't stop at waste. Modern Pringles facilities are optimizing energy efficiency through LED lighting, variable frequency drives on motors, and smart climate control systems that adjust airflow based on production load. Water used for cleaning is recovered in greywater systems. Solar panels are increasingly being added to roofs to offset peak energy usage during day shifts. Through this carefully choreographed sequence of machines, materials, software, and sanitation, millions of Pringles cans are produced each day, all identical in shape, taste, texture, and crunch. From a seemingly simple snack emerges one of the most standardized and technically refined food production systems in the industry. A Pringle isn't just engineered for flavor, it's engineered for repeatability. As Pringles production ramps across continents, the factory processes remain largely uniform, but the flavors do not. While the foundational chip recipe is remarkably consistent from one country to the next, flavor development is where regional preferences and culinary creativity come alive. From seaweed in Japan, to paprika in Germany, to chicken tikka masala in the UK, the Pringles lineup is a testament to how food science adapts to global taste trends without compromising product structure. The development of new flavors starts at specialized flavor research and development centers, often housed within or adjacent to major production facilities. These flavor labs are equipped with pilot-scale processing lines that mirror the main production environment, but in miniature. Here, food scientists and flavor chemists experiment with combinations of spices, acids, aromatic oils, and flavor precursors, blending them into fine powders that can be dry applied or oil dispersed for coating. The process begins with a flavor brief, a document informed by market research, consumer data, and regional food trends. For example, in Southeast Asia, there's a growing demand for heat, umami, and fermented flavors, whereas North American markets favor bold, smoky, and cheese-forward profiles. Once the flavor direction is defined, formulation begins. This involves building the flavor in layers: top notes, middle notes, and base notes. These powders are then micro-tested in pilot seasoning drums using small batches of real Pringles. A cross-functional team of experts, including sensory scientists, marketing professionals, and regional representatives, sample the chips in structured sessions. Evaluations are made not only on flavor intensity and balance, but also on how the seasoning adheres, how it evolves during chewing, and whether it leaves any residual texture or off notes. To quantify this, descriptive sensory analysis is used. Trained panelists score each chip along standardized scales. For example, sourness, saltiness, umami, flavor longevity, and clean finish. These scores are matched against existing products and flavor targets to determine whether the new blend is viable. Adjustments are made repeatedly. A flavor might need more lactic acid for tang, less maltodextrin for stickiness, or more encapsulated compounds to preserve aroma during frying. Once a flavor passes these internal benchmarks, it's subjected to consumer testing. Often conducted in controlled booths or simulated living rooms, participants sample the chips blindly and provide feedback on liking, uniqueness, and purchase intent. Only the highest scoring candidates proceed to production scale rollout, and even then, factory adaptations are needed. New flavors may require adjustments in drum angle, rotation speed, or seasoning flow rate to achieve even coverage without waste or dust buildup. Interestingly, not all flavors can be produced on the same lines without risk. Facilities follow strict allergen management procedures. For example, cheese-based flavors often contain milk derivatives and must be run on separate lines or in dedicated shifts with full clean-out protocols between runs. Flavor dust may linger in filters or ducts, so cross-contamination risks are carefully managed through scheduling, deep cleaning, and validation swabbing. Once production begins, logistics take over. Distribution is a global operation. From factories in the US, Europe, and Asia, Pringles are shipped to more than 140 countries. The logistics chain is engineered to minimize time between production and shelf while protecting product integrity. Pallets are stored temporarily in automated storage and retrieval systems, massive, high-density warehouses controlled by software that manages FIFO protocols and precise temperature conditions. From there, transport trucks are loaded for regional delivery. In most climates, Pringles can be shipped in ambient dry vans as long as the temperature remains below 30 degrees Celsius. However, in hotter regions or during summer months, climate-controlled containers are used to prevent oil migration, flavor deterioration, or packaging distortion caused by heat. As a product reaches retailers, the packaging does more than just protect, it sells. The Pringles canister has undergone subtle yet meaningful changes over the years. Originally designed for durability and storage, it has been adapted for visibility and ergonomics. Modern designs feature bold color blocking, QR codes for promotions, and tamper-evident seals in some countries. In-store, Pringles are often displayed vertically to highlight their stackability, or horizontally to emphasize flavor variety. Multi-pack bundling strategies vary by region. In North America, shrink-wrapped tri-packs are common. In Europe, tray displays dominate, and in Asia, minican multi-flavor assortments are especially popular among younger demographics. Parallel to the consumer-facing systems, there's a silent but powerful force ensuring Pringles quality. Shelf life stability testing. In dedicated labs, accelerated aging chambers expose Pringles samples to high humidity, elevated temperatures, and UV light. These conditions simulate long-term storage to test how the chip's texture, flavor, and aroma evolve over time. Chemical analyses measure oxidation markers in the oil. Sensory panels check for flavor loss, stale notes, or rancidity. Packaging engineers also test barrier properties of the canister, evaluating oxygen transmission rates, moisture vapor transmission rates, and mechanical integrity. The rigid tube structure gives Pringles an advantage over bagged snacks in this area, but continuous improvement efforts focus on reducing material usage while maintaining performance. Sustainability teams investigate new liner films and lid materials to improve recyclability without compromising shelf life. Meanwhile, every Pringles manufacturing facility operates with a documented traceability system. If a single issue is reported, say a foreign object or off flavor, teams can trace the affected batch back to its raw material inputs, processing line, timestamp, and even the maintenance records of involved equipment. This level of accountability is not just for crisis management, it's also a pillar of continuous improvement under Lean or Six Sigma methodologies. Plant managers review key performance indicators daily, tracking metrics like yield efficiency, chip breakage rate, seasoning variance, and energy usage per ton of product. Teams hold daily Gemba walks, on-the-floor audits, where operators and supervisors jointly inspect equipment, cleanliness, and line balance. This close attention to detail helps ensure that every Pringle, from the first to the last in the tube, is as perfect as the brand promises. This dedication to operational excellence supports global expansion. In newer markets, Pringles are often co-manufactured with partners who undergo extensive onboarding and validation audits to match the parent company's process control standards. These partners receive the exact mold geometry, dough specifications, seasoning formulas, and quality test protocols to replicate the product faithfully, no matter where in the world it's produced. As the product circulates through global supply chains, consumer feedback plays an increasingly important role. Online reviews, customer service inquiries, and social media sentiment are continuously analyzed by AI tools that flag trends, positive and negative. If flavor fatigue emerges or a packaging flaw becomes evident, insights are routed back to R&D and production teams. In some cases, limited-time flavors are revived based on nostalgia or regional demand spikes, giving rise to special editions like Buffalo Ranch, Pizza Supreme, or Hot and Spicy Jalapeno. This agile, responsive production model allows Pringles not only to maintain its core consistency, but also to evolve. The ability to innovate at scale without compromising the chip's fundamental identity is a core part of its success. If there's one feature that sets Pringles apart from every other chip on the market, it's their shape, the hyperbolic paraboloid. This unique, saddle-like curve isn't just for aesthetics, it's a product of meticulous structural engineering, specifically designed to deliver maximum stacking efficiency, uniform frying, and a signature mouthfeel unlike any flat or crinkle-cut chip. The curvature allows each chip to nest perfectly into the next, eliminating air pockets and wasted space in the canister. This design minimizes breakage during shipping and provides the visual appeal of a clean, organized stack. But it goes deeper than logistics. The curve also impacts how the chip fractures during the bite. Unlike irregular chips that snap inconsistently, Pringles break with a clean, predictable crunch. This fracturing behavior is something food texture scientists study intensely, using acoustic and mechanical analysis. In fact, the crunch curve of a Pringle is measured by placing a chip under a pressure gauge fitted with sound sensors. The chip is compressed until it breaks, and both the pressure profile and the acoustic signature are recorded. A good Pringle has a quick, brittle break with minimal flex, translating into that unmistakable first bite sensation. If the chip bends too much before breaking, it feels stale. If it's too brittle, it shatters into crumbs instead of neat fragments. This attention to mechanical bite quality is supported by consistent thickness, oil content, and starch structure, all regulated at every stage of production. Even the dough's amylose to amylopectin ratio is fine-tuned during potato flake selection and mixing, influencing how the chip cooks, colors, and crisps. But beyond shape and sound, there's also the Pringles mouth melt. As the chip dissolves, the oil, salt, and flavor particles spread evenly across the tongue, engineered to deliver a balanced flavor wave. First salty, then tangy, then savory or spicy, depending on the variant. This progression is no accident. It's the result of controlled particle sizing in seasoning powders, fat coating mechanisms, and even saliva-soluble flavor compounds embedded in the chip matrix. The result is a snack that engages multiple sensory systems at once: crisp auditory feedback, light mechanical resistance, aromatic release, and lingering taste. This multisensory synchrony is a big part of why consumers find Pringles both addictive and oddly satisfying. It's also what makes them so instantly recognizable. Without even seeing the logo, people know they're eating a Pringle the moment they hear that first crunch. It all begins long before a Dunkin' Donut ever meets a customer's lips. The journey of a factory-made Dunkin' Donut starts in massive industrial facilities engineered specifically for high-throughput baking and frying. Unlike the fresh, hand-prepared donuts in local bakeries, the factory-produced donuts that supply regional distribution centers or large retail outlets are the result of a tightly choreographed sequence of automated, mechanized operations, each designed to maximize consistency, food safety, and output volume. The core ingredients of a Dunkin' Donut seem simple: wheat flour, sugar, yeast or chemical leavening agents, eggs or egg solids, milk derivatives, oil, and water. But each of these components must meet stringent specifications. The wheat flour is typically sourced from large milling operations and arrives at the factory in bulk pneumatic tankers. Once offloaded into giant silos, it's carefully monitored for protein content, moisture, and particle size. These parameters are crucial as they directly affect gluten development, dough elasticity, and fry stability. The sugar, often in fine granulated form, is similarly delivered in bulk and stored in temperature-controlled hoppers to prevent clumping. The yeast, which may be active dry or instant, is carefully handled to maintain viability. For cake-style donuts, chemical leaveners such as sodium acid pyrophosphate and baking soda replace yeast, requiring exact dosages to control rise, texture, and batter pH. Liquid ingredients like water and milk concentrates are pumped from stainless steel reservoirs through filtered lines. Egg solids, whether powdered or liquid, are introduced via sealed containers to reduce contamination risk. At the heart of the process is the dough preparation system. In a typical yeast-raised donut line, a computerized batching system automatically dispenses pre-weighed quantities of dry and wet ingredients into a horizontal spiral mixer, usually a high-capacity unit capable of mixing several hundred pounds per batch. This mixer blends the ingredients through a timed, multi-speed cycle, a slow initial mix to hydrate the flour, followed by a high-speed kneading phase to develop the dough's structure. Temperature probes ensure the dough reaches the optimal final mix temperature, often around 78 to 82 degrees. Any deviation can alter fermentation speed and finished product quality. Once mixed, the dough is transferred, either manually in smaller setups or via automated dough elevators in large-scale operations to intermediate proofing cabinets. These are large chambers that maintain a warm, humid environment, typically around 90 degrees Celsius, with 85% humidity. The dough rests here for 30 to 45 minutes, allowing initial yeast fermentation to begin. This resting period improves extensibility and relaxes the dough for sheeting. From the proofing cabinet, the dough moves to the sheeting line. Here, massive rollers flatten the dough to a precise thickness, often controlled by laser-guided sensors. A conveyor belt feeds the dough through a series of increasingly fine rollers, each pressing it thinner until it reaches the exact gauge required for donut formation. Dusting flour is automatically sprinkled to prevent sticking, and scrap management systems collect unused dough trimmings to be reprocessed in future batches. Next, the formed dough sheet moves to the rotary cutter station. This is where the signature donut shapes come to life. Custom-designed rotary dies stamp out rings, holes, or specialty shapes like filled bars or seasonal themes. Each cutter is precision machined to minimize dough stress, ensuring even fry results. A vacuum system gently lifts and removes cut donuts from the scrap dough matrix, depositing them onto another conveyor in perfect alignment. These unbaked, shaped donuts are then transferred to the final proofer, a massive multi-tiered system that can resemble a vertical carousel. Moving slowly through this enclosed environment, the donuts are proofed for anywhere from 35 to 60 minutes, depending on product type and yeast activity. This is a critical phase. The dough expands, air cells develop, and the signature light texture of a yeast donut forms. Relative humidity and temperature are tightly regulated to promote even rising. Once proofed, the donuts enter the fryer. This is one of the most visually captivating moments in the factory. Rows upon rows of pale, risen dough transforming into golden brown perfection. Industrial donut fryers are long, shallow troughs filled with high-stability frying oil, typically a blend of soybean or palm oil designed to withstand high temperatures without breaking down. The donuts enter via an automated conveyor that gently lowers them onto the surface of the hot oil, held between 350 to 375 degrees. Floating racks or submerged mesh baskets keep the donuts evenly spaced and ensure uniform frying on both sides. The donuts are flipped halfway through using automated paddles or turning bars, so each side receives equal exposure. Fry time is typically 90 to 120 seconds per side for yeast-raised varieties. Throughout the fryer, oil filtration and replenishment systems remove debris and maintain oil quality, critical for flavor, texture, and food safety. After frying, the donuts move onto a draining belt where excess oil is wicked away using absorbent conveyor surfaces or air knives. From there, they transfer directly to a cooling tunnel, an enclosed, climate-controlled conveyor that gently brings the donuts down to ambient temperature. This cooling phase, usually lasting 8 to 12 minutes, stabilizes the structure and prevents condensation before glazing or filling. Now comes one of the most iconic steps: glazing. The donuts pass beneath a cascading curtain of warm glaze, typically made of powdered sugar, water, and stabilizers like corn syrup or mono and diglycerides to ensure sheen and viscosity. The glaze is held at precise temperatures, around 105-115 degrees Fahrenheit, to allow smooth coating without excessive dripping. Any glaze runoff is collected, filtered, and reused within quality limits. For filled donuts, a separate line handles injection. This is a precise, high-speed process where each donut is clamped and filled through nozzles that inject jelly, cream, custard, or other fillings. Volumetric pumps control exact fill amounts, typically between 15 to 25 grams per donut, to ensure uniformity. The timing of this step depends on whether the donut is glazed before or after filling, a decision made based on the type of coating or desired product appearance. Topped donuts, such as Boston cream or chocolate frosted, pass through enrobing units or individual depositor stations. These machines spread or pipe icing onto the surface, using rotating drums or mechanical arms to achieve even distribution. Sprinkles, nuts, or other toppings may be applied via shaker systems or robotic garnishing heads, with vacuum sensors ensuring no foreign objects are introduced. Once coated, the donuts continue on conveyors to the packaging area. Here, an optical vision system inspects each unit for shape, color, topping placement, and fill integrity. Defective products are automatically rejected and diverted for analysis or disposal. The acceptable donuts proceed into robotic tray loaders or auto packing machines. For bulk shipments, donuts may be arranged in plastic trays stacked into crates. For retail packs, form-fill seal systems wrap donuts in individual or multi-unit blister packs using heat-sealed film. Each packaged unit receives a date code and product identifier via inkjet printer or laser etching. Metal detectors and X-ray scanners stand guard just before final packaging to catch any foreign materials, from metal fragments to hard plastics. At this point, the product has passed through over a dozen safety checks, far more rigorous than what a local bakery could feasibly achieve. Before leaving the factory, pallets of donuts are weighed, logged, and tagged with RFID labels for inventory tracking. They're stored in temperature-controlled staging areas until trucks arrive. Distribution fleets, often operated by third-party logistics firms, are designed to transport the donuts quickly to regional warehouses or direct-to-store delivery networks. Because many factory-made donuts are frozen for extended shelf life, refrigerated trucks or freezer compartments maintain ideal storage conditions throughout transit. Once at a distribution center or store, the donuts are thawed if necessary and either resold in packaged form or used to stock fresh counters in Dunkin outlets. Some outlets may perform final finishing touches, like adding fresh glaze, sugar dusting, or customized toppings. But the bulk of the preparation has already occurred at the factory, where industrial consistency reigns supreme. Before a Subway sandwich ever reaches the customer's hands, its journey begins far from the store counter, in sprawling, high-efficiency food manufacturing plants that are responsible for producers with capacities reaching up to 1,000 pounds per batch, perform a sequence of low-speed and high-speed kneading to develop the gluten network necessary for Subway's springy, chewy bread texture. Temperature-controlled water and chilled mixing bowls help maintain the dough temperature, typically around 78 degrees Celsius, essential for proper fermentation. After mixing, the dough is unloaded onto transfer belts and sent into a first stage resting tunnel or intermediate proofer. Here, the dough rests in a humid, warm environment to allow the yeast to activate and create carbon dioxide, giving the dough extensibility before shaping. Next, the dough is portioned using volumetric dividers that slice the mass into uniform weights. These pieces then pass through rounding and molding machines that elongate them into the familiar Subway sandwich roll shape. Automated flour dusters and non-stick belts ensure smooth passage through the shaping process. For breads with toppings like oats or cheese, the dough passes under a rolling applicator or static sprinkler before entering the next proofing stage. The proofing phase is critical. Dough pieces are placed onto pans and loaded into an industrial proofer, a large, climate-controlled chamber with tiered racks or chain-driven carriers. Inside, the bread rises for 45 to 60 minutes at around 90 degrees Celsius with high humidity. Dough height, elasticity, and fermentation rate are monitored using sensors or inline imaging to guarantee uniform rise. Once proofed, the dough pans move into the par baking ovens. These are tunnel or rack ovens heated to approximately 420 degrees. The bread bakes for about 8 to 10 minutes, enough to set the structure and crust, while preserving enough internal moisture so it can be finished baking in store. After baking, the loaves are cooled in ambient air tunnels before being packaged. Packaging is a delicate process. The cooled loaves are inserted into specially ventilated film or bulk freezer trays. Modified atmosphere packaging may be used to extend shelf life and prevent freezer burn. All packaging is date-coded, labeled with batch tracking, and sent through metal detectors or X-ray systems. Then the bread is quickly frozen in blast freezers that bring core temperatures below zero in under 90 minutes, preserving quality for shipment. While the bread is handled this way, meat and poultry ingredients follow a parallel but very different industrial route. Subway's deli-style meats, turkey breast, ham, roast beef, and chicken strips are cooked, sliced, or formed in specialized meat processing plants. These facilities receive USDA-inspected raw proteins that are boned, trimmed, and cleaned under strict sanitary guidelines. The raw meats are portioned, tumbled, and marinated with Subway's proprietary brine formulas, which often include salt, phosphates, sugar, and flavorings. In the case of chicken strips or patties, the meat may be fully cooked in steam ovens or grill presses, then flash frozen to lock in moisture. Roast beef and turkey, on the other hand, are typically cooked in steam ovens or combi ovens that simulate traditional roasting while maintaining high throughput. Once cooked, the meats are cooled using spiral chillers or glycol plate systems, then sliced on high-speed rotary slicers for uniform thickness. These slices are stacked and portioned by weight using automated weighing machines, then sealed in vacuum pouches or controlled atmosphere trays. Each portion is sealed with batch coating and passed through inspection systems before being packed into cartons and frozen for distribution. Cheese slices, Swiss, American, provolone, and pepper jack are produced using high-speed forming and slicing systems. Cheese blocks are first melted down, then reformed into large sheets which pass through slicing blades and portion conveyors. Anti-stick sheets are often placed between slices, and stackers organize the cheese into count-specific bundles, each packaged under vacuum or gas-flushed atmospheres to preserve shelf life and prevent molding. Vegetables such as lettuce, tomatoes, cucumbers, onions, and green peppers are not grown in factories, but they do undergo industrial preparation before arriving at each store. Lettuce, for example, is harvested, washed with chlorinated or ozonated water, and shredded in high-speed slices. Tomatoes are cleaned, visually inspected, and machine sliced before being layered between food-safe pads that prevent bruising during shipping. Onions are peeled, sliced, and packaged in gas-flushed bags to reduce spoilage and preserve freshness. All vegetables are packed in refrigerated, ready-to-use formats and delivered through cold chain logistics to ensure they remain crisp and safe for consumption. Subway's specifications for produce are among the most rigorous in the QSR industry, often requiring vendors to perform multiple microbial tests before product release. Sauces, ranch, Chipotle Southwest, mayonnaise, mustard, sweet onion, and many others are made in liquid processing plants that function much like beverage or dairy factories. These facilities handle emulsion preparation in large mixing tanks fitted with high shear homogenizers. Ingredients like oils, water, spices, thickeners, and preservatives are blended under vacuum to ensure air-free, stable emulsions. The sauces are then pumped into sterile filling machines that dispense measured volumes into squeeze bottles, bulk pouches, or portion cups. Heat sealing, tamper-evident caps, and nitrogen flushing preserve shelf life. Every component, from bread to sauce, is designed with logistics and final assembly in mind. Once all the parts are complete, they're loaded onto pallets, sorted into refrigerated and frozen shipments, and transported to Subway's distribution centers. From there, truck routes are carefully scheduled to ensure timely delivery to to thousands of store locations. All products are scanned, tracked, and recorded during shipment, ensuring cold chain integrity and traceability from plant to sandwich counter. Inside the store, the staff becomes the final assembly line. Each morning, the frozen bread dough is thawed and given a second proof before finishing its bake in the store's convection ovens. Meats are defrosted and held in refrigerated bins, vegetables are placed into prep trays, and sauces are opened and loaded into squeeze bottles. Sandwich artists follow precise build sheets and portioning guides to ensure a consistent experience for the customer. Even at the store level, there are echoes of the factory's precision. How many ounces of lettuce per 6-inch sandwich? How many slices of meat? What angle to cut the bread? It all comes back to what was engineered upstream. Without the highly standardized processes in the manufacturing plants, the in-store experience wouldn't feel as predictable and familiar across the world. The industrial journey of a Chipotle meal begins with ingredient sourcing. Chipotle is known for its emphasis on food with integrity, which means that much of the upstream processing is tightly controlled, even before the factories get involved. The chain sources meats that are often antibiotic-free, pasture-raised, or sustainably farmed. These meats arrive at centralized processing plants, some Chipotle-operated, others contracted to third-party co-packers, with exacting specifications. Take chicken, for instance, one of Chipotle's most popular proteins. Whole chicken breasts and thighs are delivered from certified suppliers in refrigerated transport and immediately placed into cold storage bays at the processing facility. These facilities are equipped with advanced sanitation systems, including antimicrobial entry zones and HEPA-filtered air circulation to maintain a sterile environment. The chicken is deboned, trimmed of excess fat, and portioned into standardized sizes using automated cutters. Optical sorters with high-speed cameras and laser detection systems inspect each piece for defects, bone fragments, or inconsistencies. After cutting, the chicken moves into industrial tumblers or vacuum mixers where it is marinated. The marinade consists of oil, spices, garlic, citrus juices, and chipotle pepper, all pre-mixed in large blending tanks. These tumblers are designed to evenly coat the chicken while tenderizing it, using a slow rotational motion that lasts anywhere from 20 minutes to several hours, depending on the specific formulation. The chicken is then sealed into vacuum-packed pouches or bulk containers and flash-chilled. In many cases, the chicken is shipped raw to Chipotle locations, where it is grilled fresh daily. However, in higher volume markets or during peak operational periods, some portions may be pre-cooked using commercial-grade combi ovens or grill presses inside regional commissaries. These ovens are steam-injected and heat-distributed, ensuring that the chicken reaches internal temperatures of 165 degrees without losing moisture. After cooking, the chicken is cooled through rapid chill spiral systems that reduce the temperature below 40 degrees in less than 90 minutes, in compliance with USDA food safety standards. Now let's move to beef, specifically the barbacoa and steak options. These are handled in meat facilities equipped to manage tougher cuts like shoulder clod or round for barbacoa, and sirloin or top butt for steak. The barbacoa beef is typically seasoned, seared, and slow cooked in massive steam kettles or pressurized braising tanks. These tanks operate on programmable logic controllers that maintain precise temperatures and cook times, allowing the meat to tenderize while absorbing the bold, chipotle, and cumin flavors characteristic of the dish. Once fully cooked and shredded by automated paddles, the barbacoa is portioned into pouches and vacuum sealed. It's then rapidly frozen using cryogenic tunnel freezers, often with liquid nitrogen or CO2, to preserve texture and moisture content. Steak, on the other hand, may be seared and sous vided, then chilled and packaged for final grilling in store, allowing for that signature charred flavor upon finishing. Beans, both black and pinto, are another central component of Chipotle's offerings, and their factory preparation is highly systematic. Dry beans are received in bulk sacks and stored in silo bins, where they undergo cleaning, sorting, and rinsing. Industrial bean cookers, large rotating steam kettles or pressure vessels, hydrate and cook the beans using temperature and pressure sensors to ensure that every batch hits the ideal softness and moisture level. Chipotle's beans are often seasoned with bay leaf, garlic, cumin, and salt, and held in stainless steel jacketed tanks for blending. After cooking, beans are cooled, portioned into food-safe containers or sealed bags, and transported under refrigeration to stores, where they are reheated and seasoned further before serving. Some regional commissaries may do the final seasoning step in-house, using proprietary spice blends and steam kettles to reduce in-store labor. Next up is the rice, a deceptively simple but carefully controlled product. Chipotle's cilantro lime rice, white or brown, begins with high-grade long-grain rice sourced from domestic or South American suppliers. At the processing plant, the rice is rinsed to remove excess starch and then batch cooked in industrial steamers or pressure rice cookers. These machines are equipped with moisture and temperature sensors to maintain the exact texture and doneness that Chipotle requires. Fluffy, but not mushy, firm, but not undercooked. Once cooked, the rice is transferred to large mixing bowls where lime juice, chopped cilantro, and salt are added. Some facilities add a touch of oil for separation and sheen. Pneumatic arms or food-safe agitators mix the rice gently but thoroughly. From there, it is either packaged hot for immediate shipment or chilled using blast chillers, and packed cold for later reheating in-store. Salsas, like the mild tomato salsa, corn salsa, and spicy red chili version, are produced in facilities that combine both fresh vegetable processing and sauce manufacturing capabilities. Roma tomatoes, tomatillos, onions, and jalapenos are washed, diced, and de-seeded by high-speed dicers equipped with antimicrobial wash cycles. The chopped ingredients are portioned into blending tanks, where citrus juice, cilantro, salt, and spices are added. These tanks are chilled to preserve freshness during mixing. The salsas are filled into containers using multi-head fillers, which ensure precise weight and avoid overfilling. Each container is lidded, labeled, coded, and passed through X-ray or metal detection systems before being boxed and shipped under refrigeration. Because Chipotle prides itself on using fresh, preservative-free salsas, the cold chain must be rigorously maintained, and shelf life is generally short, often under 7 days. Guacamole is arguably one of Chipotle's most iconic items, and it, too, is partially factory-produced to reduce in-store prep time. Avocados are shipped to processing plants where they are ripened in ethylene-controlled ripening rooms. Once they reach optimal softness, they are halved, pitted, and scooped using semi-automated systems. Some facilities still rely on manual scooping to preserve texture and quality. The avocado pulp is then mixed with red onions, cilantro, lime juice, salt, and jalapenos in large mixing vessels outfitted with slow-speed paddle blades to avoid over-pureeing. The finished guacamole is portioned into food service containers and sealed under nitrogen-rich modified atmosphere packaging to prevent oxidation. These are chilled and shipped directly to stores, where they are used within a few days. Even toppings like shredded cheese and lettuce are processed off-site. Cheese blocks, such as Monterey Jack and white cheddar, are shredded using rotary shredders that minimize clumping and deliver consistent length and thickness. The shreds are dusted stretches back to the early 1980s, when they were first introduced to the market as a playful, intensely flavored treat unlike anything else in the candy aisle. The appeal lay in their irregular shapes, their bright colors, and their signature combination of sweet and sour notes. Behind the scenes, however, the magic is created not by whimsy, but by a carefully controlled industrial process. It all begins with the sourcing of raw ingredients. The foundation of nerds is refined cane or beet sugar, which arrives at the factory in bulk deliveries, often in multi-ton silos or in large paper sacks that are emptied into storage hoppers. This sugar is highly refined to ensure purity, with a moisture content so low that it will not clump during storage or handling. Alongside the sugar come shipments of corn syrup, which acts as a binding and texturing agent, as well as citric acid and malic acid to provide the tartness that defines Nerd's flavor profile. The plant also receives concentrated flavor oils and powdered colors approved for food use. Each batch of these ingredients is tested in a quality control laboratory before it enters the production stream, ensuring compliance with both flavor and safety standards. The production of Nerds begins with a core, which is essentially a tiny granule of sugar that serves as the seed for the candy's build-up process. These seed crystals are often derived from slightly coarser sugar grains that have been screened to a uniform size. The real artistry begins in the heart of the coating pans, large rotating drums that are the beating heart of sugar candy manufacturing. Inside these stainless steel pans, the sugar seed crystals are gently tumbled as a fine mist of sugar syrup is sprayed over them. This syrup is prepared in a heated mixing tank, where granulated sugar is dissolved into water under controlled temperature, often in the range of 110 to 130 degrees Celsius, and then blended with a precise amount of corn syrup to control crystallization. The hot syrup flows through jacketed piping to prevent premature cooling before being atomized into a fine spray within the coating pan. As the syrup coats the tumbling seed crystals, it begins to harden upon contact with the cooler air inside the pan, forming a thin outer layer. Then, a light dusting of dry sugar is sometimes added to further build the surface and maintain separation between individual granules. This cycle repeats dozens or even hundreds of times, each layer adding microns of thickness to the growing candy piece. Operators closely monitor airflow, humidity, and drum rotation speed to ensure that the candies do not stick together or form unwanted lumps. During this stage, the irregular shapes that make Nerds so distinctive begin to emerge. Unlike machine-molded candies that have identical geometry, these sugar-coating pans produce slight variations in size and contour, which means every Nerd has its own unique outline. The gradual layering process continues until the candy reaches the target size, which is typically just a few millimeters in diameter. Once the base size is achieved, flavoring and coloring are introduced. This is a delicate operation, as liquid flavors and colorants must be distributed evenly without dissolving the sugar surface. The pan operator reduces airflow slightly and sprays a concentrated solution of flavor oils, acids, and color onto the candy bed. In many cases, flavors are applied in small incremental sprays with pauses for tumbling in between, allowing the surface to dry and preventing color streaking. The flavors are carefully balanced so that the acids provide tang without overwhelming the sweetness, creating the signature taste that fans recognize instantly. After flavoring and coloring, the candies undergo a polishing step. This involves applying a thin layer of glazing agent, such as carnauba wax, which gives the Nerds their characteristic sheen and helps protect them from moisture pickup during storage. The glaze is applied in a separate polishing pan, where candies are tumbled with a small amount of the molten wax until every piece has a uniform shine. At this point, the candies are allowed to cool and set fully, ensuring that their coatings have hardened completely. Cooling may occur in ambient air or in a temperature-controlled chamber that maintains low humidity to prevent stickiness. The fully cooled candies are then transferred via gentle vibratory conveyors to the packaging area. The packaging operation for Nerds is an impressive example of precision weighing and high-speed filling. Because the candy pieces are so small and irregular, multi-head weighers are commonly used to ensure accurate portioning. These machines use multiple load cells arranged in a circular pattern, dropping small amounts of candy from each channel until the combined total matches the target weight. This system minimizes giveaway and ensures that each box contains exactly the promised amount. The iconic Nerds boxes are constructed from food-grade cardboard with an inner lining that protects against moisture. The packaging line begins by folding and gluing the flat-printed cartons into their box shape, often with automated carton erectors that can handle hundreds of units per minute. The weighers then deposit the precise quantity of candy into each box through stainless steel chutes. For dual flavor boxes, a partition is inserted inside the carton, and two separate weighing heads feed different candies into each side simultaneously. Once filled, the boxes pass through a closing station, where flaps are folded and glued shut, followed by a coding station that prints lot numbers and best before dates for traceability. The sealed boxes are then collated into larger trays or shrink-wrapped bundles for ease of handling in distribution. Quality control continues all the way through the process. In addition to the raw ingredient checks at the start, samples of candy are pulled from the line at regular intervals to assess flavor consistency, color uniformity, and physical integrity. The hardness of the coating is measured with specialized instruments, and the acidity levels are checked to ensure the sourness remains within the brand's signature profile. Metal detectors are integrated into the conveyor system to ensure no foreign materials make their way into the final product. From the packaging area, the candies move to the warehouse for distribution. Since Nerds are low in moisture and have a hard sugar shell, they are relatively stable during storage. However, they are kept in a cool, dry environment to maintain their texture and prevent color fading. Pallets of finished product are wrapped and staged for shipment to wholesalers, retailers, and export markets around the world. The journey from sugar seed to the vibrant, tangy pellets in your hand is a testament to how much engineering is hidden inside even the simplest candies. Each step, from syrup spraying in massive tumbling pans to the delicate flavor infusion and high-speed filling lines, is executed with precision to deliver the playful, crunchy experience that has kept Nerds popular for decades. Over time, manufacturing technology for Nerds has evolved to improve efficiency and consistency. Early production relied heavily on skilled operators adjusting pans by sight and sound. Today, advanced automation systems track humidity, airflow, and syrup application rates with sensors and feedback loops, ensuring that every batch meets exacting standards. The result is a product that remains faithful to its original flavor and texture while benefiting from modern advancements in food processing equipment. There is also increasing focus on sustainability in candy production. Many factories now recover and reuse heat from syrup cooking kettles, implement water-saving cleaning systems for coating pans, and work with suppliers to source sugar from more sustainable agricultural operations. Packaging too is being reevaluated, with lighter materials and improved recyclability being considered for the future. What makes the production of Nerds especially fascinating is the balance between art and science. The process is rooted in classical confectionery techniques that date back centuries, yet it is executed on a scale and with a precision that only modern machinery can achieve. The slight variations in size and shape that give Nerds their charm are not flaws, but deliberate results of the panning process, embraced as part of their identity. The story of Twizzlers begins long before the candy reaches the factory floor. As with many mass-produced confections, the foundation is in the sourcing of high-quality raw materials. The primary ingredient is refined wheat flour, which gives Twizzlers their chewy, slightly bread-like texture. This flour arrives at the plant in bulk tanker trucks and is stored in towering silos that protect it from moisture and contaminants. From here, it is gravity-fed or pneumatically conveyed through sealed pipes to the mixing area. Alongside flour, the recipe calls for corn syrup, which provides sweetness, binding power, and flexibility, as well as sugar. which boosts flavor and adds structure. Vegetable oil, often in the form of soybean or palm oil, contributes to the mouthfeel, while food-grade colors and flavorings give Twizzlers their signature appearance and taste. Every ingredient undergoes rigorous inspection in the quality control laboratory before it can be released to production. Flour samples are checked for protein content and moisture levels. Sugar is screened for crystal uniformity, and corn syrup is tested for viscosity and purity. Liquid flavors and colors are reviewed for consistency against reference standards. Once approved, ingredients move into the blending stage, where the transformation from raw material to candy dough begins. The mixing process takes place in large stainless steel horizontal mixers fitted with heavy-duty paddles or spiral blades. The operation starts with a precise ratio of flour and sugar being combined, followed by the gradual addition of corn syrup and water. These mixers operate under controlled speeds to ensure the dough develops evenly without excessive heat buildup. Oil is incorporated next, coating the flour particles and contributing to the dough's smooth, pliable consistency. Throughout mixing, operators monitor temperature and dough texture, making small adjustments to moisture content if necessary. In many plants, this step is partially automated, with sensors tracking torque resistance in the mixer to determine when the dough has reached the ideal elasticity. Once mixed, the candy dough is transferred to the extrusion line. This is the stage where Twizzlers take on their famous twisted rope form. The dough is fed into a large extruder, essentially a high-powered screw press that forces the material through a specially designed die. The screw inside the extruder rotates at a controlled speed, kneading and pushing the dough forward while maintaining an even temperature to prevent premature setting. At the end of the barrel, the die features multiple openings shaped to produce the exact cross-section of a Twizzler rope. For the classic variety, the die includes ridged channels that create the candy's spiral grooves. As the dough emerges from the die, it is still warm and soft, making it easy to shape but vulnerable to deformation. To preserve the precise geometry, the extruded ropes immediately enter a cooling conveyor, a long belt that passes through a tunnel where chilled, dehumidified air circulates. This step lowers the candy's temperature and sets the outer surface while maintaining a chewy interior. The speed of the conveyor is carefully calibrated so that cooling is uniform along the rope's entire length. An interesting detail of Twizzlers' production is that the twist in each rope is not solely a result of the die design. The conveyor belt itself may be equipped with rollers that gently rotate the ropes as they move forward, enhancing the spiral effect. The amount of twist is a delicate balance. Too much rotation can weaken the structure and cause breakage, while too little results in a less distinctive look. After cooling, the ropes are ready to be cut to size. Cutting is performed by high-speed guillotine blades or rotary knives synchronized with the conveyor movement to avoid crushing the candy. For standard snack-sized Twizzlers, lengths are typically between 6 and 8 inches, but the same line can be adjusted to produce miniature bites or extra long versions. The cut pieces now move towards the packaging area, but before they are boxed or bagged, they undergo inspection. Quality control technicians pull samples from the line to check twist uniformity, diameter, weight, and surface texture. The moisture content is measured to ensure the candy retains its chewiness during storage. Flavor is also evaluated by trained sensory panels who compare each batch to established taste profiles. Packaging Twizzlers is a study in efficiency. Depending on the product format, they may be wrapped in flexible plastic film, placed in cardboard trays, or sealed in resealable pouches. The packaging machinery begins with an in-feed system that gently aligns the ropes into uniform stacks. These stacks are then transferred into forming tubes where the plastic film is drawn around them, sealed along the edge with heat, and cut into individual packs. Heat seal jaws close the ends to lock in freshness and protect the candy from moisture and oxygen. Lot codes, manufacturing dates, and product identifiers are printed directly onto the packaging by inkjet or thermal printers, ensuring traceability for every unit. Sealed packages are collected onto a takeaway conveyor and then collated into larger cartons for shipping. These cartons are stacked on pallets by robotic palletizers, which arrange the boxes in stable patterns and wrap them in stretch film to secure the load. From here, the pallets are moved to the warehouse, a temperature-controlled environment designed to maintain product quality. Although Twizzlers are relatively stable due to their low moisture and high sugar content, excessive heat can cause surface stickiness or deformation, so storage temperatures are carefully regulated. The finished products are then shipped to distribution centers, retail outlets, and export markets. Behind all of this is a network of automation systems and process controls that keep production running smoothly. Modern Twizzlers plants rely on programmable logic controllers to coordinate mixer cycles, extrusion pressures, conveyor speeds, and packaging rates. These systems integrate with quality control data, enabling operators to adjust parameters in real time if a batch shows signs of deviation from the standard. The flavoring of Twizzlers deserves special mention. While the classic strawberry variety is the most famous, the process allows for a wide range of flavors, from cherry to chocolate to licorice. In each case, the flavor oils are blended into the dough at the mixing stage to ensure even distribution. The choice of flavor affects other parameters as well. For example, chocolate varieties may require a slightly different extrusion temperature due to the fat content in cocoa powder, while licorice varieties may use molasses or anise oil that alter dough handling characteristics. Over the years, Twizzlers production has been refined not only for efficiency, but also for consistency. Early methods required more manual handling, with operators guiding ropes off the extruder and cutting them by hand. Today's operations are highly automated, with minimal direct contact between workers and the product. This not only improves hygiene, but also allows for higher output with fewer defects. Sustainability is becoming a greater focus in candy manufacturing as well. Plants are investing in closed-loop water systems for cooling conveyors, energy-efficient ovens for any heat treatment steps, and waste reduction programs that recycle off-spec candy back into the mix when feasible. Packaging materials are also being evaluated for recyclability, with thinner films and plant-based plastics under consideration. What makes the Twizzlers process so fascinating is the combination of bakery-like dough handling with candy-making sweetness. The extrusion technology is similar to that used in pasta production, yet the ingredients and post-extrusion handling are firmly rooted in confectionery science. It is a hybrid process that demands both mechanical precision and an understanding of how sugars, starches, and fats interact under heat and pressure. When you pick up a pack of Twizzlers, you are holding the result of careful ingredient selection, finely tuned mixing and extrusion, precise cooling and twisting, and airtight packaging. Each rope is the product of countless micro adjustments in speed, temperature, and formulation that ensure the candy's texture, flavor, and appearance are exactly as consumers expect. The story of a Haribo gummy begins with the ingredients, each of which is selected for quality and consistency. At the heart of the recipe is gelatin, a protein derived from collagen that gives the candy its characteristic elastic texture. This gelatin arrives at the factory in dry, granulated form and must be carefully hydrated before use. Alongside gelatin, the formulation includes glucose syrup, often produced from wheat or cornstarch, which provides body, prevents crystallization, and contributes to the chewiness. Sugar is another mainstay, giving sweetness and structural integrity. Additional ingredients include citric acid for tartness, natural and artificial flavorings for each variety, and food-safe colorants to create the rainbow of hues that define Haribo's product line. Every batch of ingredients undergoes rigorous testing in a quality control laboratory before it reaches the main production floor. Gelatin is checked for bloom strength, which determines the firmness of the finished candy. Glucose syrup is tested for solids content and viscosity, ensuring it will flow and set properly in the cooking process. Flavor and color concentrates are measured for potency and compared against established standards. Only when the raw materials pass inspection are they released to the production team. The first major step in making Haribo gummies is the cooking process. This begins in large stainless steel vessels called dissolvers or cooking kettles. Here, sugar, glucose syrup, and water are combined and heated under controlled conditions. The heating process brings the mixture to a high temperature, often in the range of 110 to 140 degrees Celsius, allowing the sugars to dissolve completely and the syrup to thicken. Once the sugar syrup reaches the correct density, pre-soaked gelatin is added. The gelatin is never boiled, as high temperatures would damage its gelling properties. Instead, it is stirred in gently once the syrup has cooled to a safe range, typically between 80 and 90 degrees Celsius. At this point, flavorings, acids, and colors are added. For gummy bears, this might include lemon, orange, raspberry, apple, and strawberry flavor profiles, each paired with a corresponding color. The additives are metered in with precision pumps to ensure every batch is consistent in both taste and appearance. Stirring must be thorough but gentle to avoid incorporating excess air bubbles, which could mar the candy's surface. Once the mixture is fully blended, it is ready to be formed into shapes. This is where Haribo's distinctive starch molding process comes into play. The company uses a method called the Mogul system, an automated production line that allows liquid candy to be deposited into detailed molds with incredible precision. The process begins with large trays filled with a fine, dry cornstarch powder. This starch serves two purposes. It prevents the sticky candy from clinging to the trays, and it helps wick away excess moisture during the setting stage. Each tray passes through a stamping unit where metal dies press the shape of the candy into the starch. Tiny, bare outlines, cola bottle profiles, or whatever form is being produced. The impressions are crisp and exact, ready to receive the warm, liquid mixture. From the cooking kettles, the candy syrup is pumped through heated pipelines to a series of depositor nozzles. These nozzles align perfectly with the starch impressions and release measured amounts of syrup into each cavity. The depositor can switch flavors and colors quickly, allowing for multiple varieties to be produced on the same line with minimal downtime. Once deposited, the trays of liquid candy are conveyed into a long climate-controlled curing room. Here, they rest for 12 to 72 hours, depending on the recipe, temperature, and humidity. During this time, the gelatin network fully sets, giving the candy its final chewy texture, while the starch continues to absorb surface moisture. The curing rooms are kept at specific humidity levels to prevent the candies from drying out too much or becoming sticky. When curing is complete, the trays move to the demolding stage. The gummy shapes are gently lifted from the starch, which is recovered, dried, and sieved for reuse in future molding. Any excess starch clinging to the candies is removed through a combination of mechanical shaking and soft air jets. The gummies, now fully formed, have a matte appearance and a slightly tacky feel at this stage. To give them the glossy finish consumers recognize, the candies are transferred to large rotating drums called glazing pans. Inside, they are tumbled with a thin coating of food-grade waxes such as carnauba or beeswax, along with oils that enhance shine and prevent sticking. The glazing process is quick but crucial, as it also provides a protective barrier against moisture changes during storage. With their appearance perfected, the gummies proceed to the packaging area. Here, high-speed conveyors feed them into multi-head weighers, machines equipped with multiple hoppers that dispense exact amounts to achieve the target package weight. The candies are dropped into pre-formed bags or into the forming tubes of vertical form-fill-seal machines. These machines create a bag from a continuous roll of printed film. Seal the bottom, fill it with the candy, then seal the top in one continuous motion. For variety packs, sophisticated sorting systems group different gummy shapes and flavors in precise ratios before they reach the weighing step. This ensures that every bag contains the intended assortment. Packaging films are chosen for their barrier properties, keeping the gummies fresh while displaying bright branding. Each bag receives a lot code and best before date for traceability, then passes through metal detection equipment as a final safety measure. The finished bags are gathered into cartons, stacked onto pallets, and wrapped in stretch film to stabilize them for shipping. Pallets are moved to temperature-controlled storage areas until they are loaded onto trucks bound for distribution centers and retailers around the world. Throughout the entire process, quality control remains a constant presence. Samples from each batch are taken at multiple points, from syrup cooking to molding, curing, and packaging, to ensure that every aspect meets Haribo's specifications. Technicians test texture with penetrometers to confirm the perfect chew, measure pH to monitor acidity, and use colorimeters to verify hue accuracy. Flavor panels taste test samples to ensure the product matches established sensory profiles. The production of Haribo gummies has evolved significantly over the decades. Early batches were made by hand in small copper kettles and poured into starch molds one tray at a time. Today's lines can produce hundreds of thousands of pieces per hour, with computerized systems controlling every variable. Yet the core principles remain the same: quality ingredients, precise cooking, careful molding, and patient curing. There is also a growing emphasis on sustainability within Haribo's operations. Many plants now use energy recovery systems to capture heat from cooking processes, recycle starch indefinitely, and source gelatin and sugar from more sustainable supply chains. Efforts to reduce packaging weight and increase recyclability are also underway, ensuring that the joy of gummy bears has a smaller environmental footprint. What makes Haribo's process fascinating is the blend of old-world confectionery craftsmanship and high-tech automation. The mogul molding system, for instance, is an industry standard, yet it still relies on principles that candy makers have used for over a century. The long curing time is a reminder that some aspects of candy making simply cannot be rushed if the desired texture is to be achieved. By the time a bag of Haribo gummies reaches the shelf, it has undergone a transformation from raw sugar, syrup, and gelatin into a perfectly shaped, flavorful, and brightly colored treat. Behind each piece is a network of ingredient sourcing, controlled cooking, precision molding, and patient curing, all supported by layers of quality control and packaging expertise.